These are the tallest, longest, and deepest megaprojects ever created by human hands. From record-shattering skyscrapers piercing the clouds, to tunnels plunging beneath the sea, and bridges stretching beyond the horizon, each one redefines the limits of engineering. In this video, we explore the world's ultimate construction records, revealing the scale, innovation, and ambition behind humanity's most extreme creations. The Olympic and Hill Tower is rising fast in the heart of downtown Los Angeles, and when complete in 2025, it will stand as one of the tallest residential buildings in the city. Located at the intersection of Olympic Boulevard and Hill Street, this 60-story skyscraper is redefining the skyline while pushing the boundaries of vertical construction in a dense urban environment. Behind the sleek glass facade and luxury branding lies a highly engineered structure built to handle everything from seismic activity to tight logistical constraints. The tower's structural system is a reinforced concrete core surrounded by a network of shear walls and moment-resisting frames. At its base, the tower sits on a deep matte foundation, essentially a massive slab of high-strength concrete over 6 feet thick, poured in a continuous operation that lasted for more than 20 hours. This mat is supported by dozens of drilled piles reaching deep into stable soil strata, designed to resist lateral movement during earthquakes. The superstructure rises floor by floor using a jump form system, which allows the central concrete core to be poured continuously upward while maintaining access and safety for crews working on the perimeter slabs. High-strength concrete is pumped vertically through pressure lines to the top of the core, where it's poured into custom forms and cured under strict temperature and moisture conditions to prevent cracking. Around the concrete core, the tower's floor plates are cast in place using a post-tensioned slab system. This allows each floor to be thinner and lighter while still maintaining structural strength, increasing interior height without adding unnecessary mass. As each level is completed, the exterior curtain wall system follows just behind, composed of prefabricated glass and aluminum panels hoisted into place and sealed for thermal and acoustic performance. Construction in this area of downtown is tight, so staging materials and equipment is a challenge. To manage this, crews operate with just-in-time delivery schedules, and a tower crane stationed at the core handles nearly all vertical lifts from rebar cages to window panels. The crane itself is periodically jumped upward as the building rises. Olympic and Hill will include over 500 residential units, with amenities like a rooftop pool, fitness center, and commercial space at street level. Mechanical systems, including HVAC and water, are stacked vertically in dedicated shafts, with maintenance access on mechanical floors interspersed throughout the tower. Let's discuss the Foothill extension of the A-line, a $1.5 billion rail expansion project that is set to transform transit in Los Angeles County and San Bernardino County. This crucial extension aims to alleviate traffic congestion, enhance accessibility, and provide a sustainable alternative to traditional highway travel. The A-line, formerly the Gold Line, has been an integral part of the light rail network in Los Angeles for decades. Initially opening in 2003, the system has expanded in multiple phases to accommodate growing commuter demands. The Foothill extension was conceptualized as a long-term strategy to connect the eastern suburbs of Los Angeles with the broader transit network, reducing dependence on automobiles and supporting a greener transportation ecosystem. Over the years, Los Angeles County has experienced worsening traffic congestion. The highways are becoming increasingly burdened by commuters traveling between the San Gabriel Valley and downtown Los Angeles. With public transit usage on the rise and environmental concerns pushing for reduced carbon emissions, the Foothill extension was designed as a viable alternative to daily car commutes. Not only does it address mobility challenges, but it also supports regional economic growth, giving residents easier access to jobs, education, and essential services. The Foothill extension spans 9.1 miles, stretching from Glendora to Pomona, adding 4 new stations along the way. Each station is equipped with bike lanes, electric vehicle charging stations, and modernized platforms, reflecting a commitment to eco-friendly and commuter-friendly design. The new extension will also include seismically resilient bridges and tunnels, ensuring the system remains structurally sound in earthquake-prone areas like Southern California. This phase of the project will not only expand the reach of the light rail service in Metro, but it will also integrate seamlessly with existing bus networks and park and ride facilities. This rail extension is expected to increase property values and encourage denser, more walkable communities near stations. The Foothill extension is a multi-billion-dollar investment backed by local, state, and federal funding. The total construction cost has already surpassed $1.5 billion, reflecting the complexity of rail infrastructure development in dense urban environments. To ensure efficiency and precision, state-of-the-art rail laying machines and automated track monitoring systems are being used to construct the line. These advanced machines help accelerate construction timelines, maintain track alignment accuracy, and minimize disruptions to nearby communities. Specialized cranes and tunneling equipment are also being deployed to construct bridges and underground sections, ensuring durability and long-term reliability. The construction is progressing steadily, with the first segment on track for completion by 2026. However, this is only the beginning. Plans are already in motion to extend the A-line even further beyond Pomona, reaching Montclair and Ontario International Airport in subsequent phases. This future expansion will increase connectivity, offering a direct rail link from San Bernardino County to downtown Los Angeles, a game changer for commuters in one of the most traffic-heavy regions of the nation. But just wait until you hear. One of the most ambitious freeway improvement undertakings in the Phoenix metropolitan area is the Arizona Department of Transportation's Broadway Curve project, which targets a congested segment of Interstate 10. This stretch, encompassing roughly 11 miles from Interstate 17 to Loop 202, serves as a crucial artery for both commuter and freight traffic. Given the region's rapid population growth and increasing traffic volumes, the reconstruction and widening of the Broadway Curve was designed to significantly boost capacity, reduce travel time, and enhance overall safety. The project commenced with a detailed phase of geotechnical investigations and environmental clearances. Borehole drilling and soil sampling were carried out across the corridor to assess bearing capacity, subsurface conditions, and groundwater levels. These findings informed the design of retaining walls, bridge foundations, and pavement sections. Early coordination with utility companies was critical, as the corridor housed numerous high-voltage electrical lines, sewer mains, water lines, and telecommunications conduits. Each utility conflict had to be resolved through relocation or protective measures prior to major excavation activities. Construction began with the expansion of the freeway's footprint, which required significant demolition of existing infrastructure. This included the removal of aging sound walls, bridge decks, and portions of the roadway itself. To manage dust and minimize particulate emissions during demolition, crews utilized water spraying systems and mounted mist cannons. Excavated materials were sorted on site, with recyclable concrete and asphalt diverted for reuse in base courses or temporary detours. One of the project's signature features was the addition of new travel lanes and high-occupancy vehicle lanes in both directions. To accommodate this, the freeway's subgrade had to be widened, involving large-scale, earth-moving operations using scrapers, bulldozers, and graders. Where right-of-way was constrained, mechanically stabilized, earth-retaining walls were employed, with precast concrete panel facings and geogrid reinforcements layered within compacted backfill. Bridge construction was another critical aspect. Several interchanges and overpasses, including those at Broadway Road and State Route 143, were either reconstructed or newly built. Foundations were formed using cast-in drilled hole piles, and superstructures were assembled with precast concrete girders hoisted into place using hydraulic cranes during overnight closures. Concrete bridge decks were poured with embedded post-tensioning ducts to handle long-span stresses and reduce deflection. Pavement design for the mainline lanes relied on a composite structure of crushed aggregate base and Portland cement concrete chosen for its durability under heavy truck loads. Stringline guided slipform paving machines ensured precise elevation and cross slope. Adjacent auxiliary lanes and ramps used hot mix asphalt with polymer modified binders for added flexibility under thermal cycling. In parallel, new drainage systems were installed, featuring large diameter reinforced concrete pipes, catch basins, and retention basins to manage the significant runoff generated by impervious surfaces. Intelligent transportation systems were also embedded, including dynamic message signs, traffic detection loops, and closed-circuit television cameras, all linked to ADOT's Traffic Operations Center. The Loop 202 South Mountain Freeway is one of the most ambitious infrastructure undertakings in Arizona's history. Stretching over 22 miles through the southwest region of the Phoenix metropolitan area, this multi-billion-dollar highway project was engineered not just as a means of improving traffic flow, but as a complete reimagining of regional connectivity. Constructing it required navigating everything from mountainous terrain and ancient archaeological sites to urban development and complex geotechnical challenges. The alignment of the freeway cuts through three major landscape types: flat desert plains, flood-prone areas, and the rugged foothills of the South Mountain Range. Each segment demanded a unique construction approach. In the floodplain sections, engineers installed extensive drainage systems, including box culverts, retention basins, and pump stations designed to handle monsoon downpours that can drop several inches of rain in under an hour. Many of these systems are equipped with telemetry to allow real-time monitoring and remote operation. In the mountain section, a major feat of engineering was the blasting and grading through the South Mountains themselves. Controlled rock blasting had to be performed with high precision to avoid destabilizing the slopes and to minimize impacts on the surrounding environment. After blasting, large cuts were reinforced with rock bolts, soil nails, and geotextiles to prevent erosion and rockfall. Additionally, deep roadway embankments were stabilized using mechanically stabilized earth walls, modular systems that combine layers of soil and reinforcement grids tied into concrete face panels. Bridges and overpasses on Loop 202 are engineered with seismic resilience and thermal movement in mind. Phoenix's extreme heat can cause bridge decks to expand and contract significantly, so expansion joints and bearing pads were carefully selected and calibrated. Each bridge includes post-tensioned concrete girders to achieve long spans while maintaining a shallow profile, critical in areas where vertical clearance was limited by existing development or terrain. Another innovation is the use of rubberized asphalt across most of the freeway surface. This material not only reuses discarded tires, helping with sustainability goals, but also reduces traffic noise and withstands Arizona's intense solar exposure without rutting or cracking prematurely. Perhaps the most complex aspect was integration with existing traffic arteries and neighborhoods. The freeway had to interface seamlessly with Interstate 10 and local surface streets, requiring flyovers, braided ramps, and collector-distributor lanes to separate merging and exiting traffic. Throughout construction, crews employed intelligent transportation systems, including automated traffic control and variable message signs, to manage detours and maintain safety. Across the world, engineering is reaching new extremes, creating projects so massive they seem almost absurd. These are the feats that defy logic and push the limits of what was once thought possible. In this documentary, we explore the most remarkable engineering projects, showcasing colossal undertakings that reshape landscapes and even entire nations. From record-breaking railways to entire tunnel networks, witness the sheer audacity behind these incredible constructions. We have to talk about Silk City, or as it is officially called, Madinat Al Haririya. With its centerpiece, the Burj Mubarak, set to surpass Dubai's Burj Khalifa as the tallest building in the world, Silk City is shaping up to be a marvel of modern engineering and design. Silk City isn't just about one towering skyscraper. It's an entire city designed from the ground up to become a hub of innovation, luxury, and sustainability. There are 4 different districts it is divided into. One of the most exciting features associated with Silk City is Burj Mubarak, a skyscraper of 1,001 meters, inspired by the legendary tales of Arabian Nights. The building is designed to accommodate 7,000 residents, and it will also have triple-decker elevators for easy and efficient movement in the skyscraper. Major ones are the Sheikh Jaber Causeway, a fine engineering work joining Silk City to Kuwait City. Spanning a colossal length of 36 kilometers from the head of Kuwait Bay, it doesn't just shorten travel time, it joins Silk City closer to the nation's heart. So, why does Silk City represent a big deal? First, it is very bold for Kuwait to diversify its economy from purely oil-based reliance. Kuwait relies heavily on crude oil revenues. Now, as neighbors such as Dubai and Saudi Arabia have commenced serious investment into non-oil sectors, this emulates others. Silk City forms part of this strategy, where Kuwait would position itself as a regional hub for trade, finance, and tourism. This will create a connection between Kuwait and the rest of the countries, where China, Iraq, and Iran will be added to the relationship economically. The city also transverses along the path of the China Belt and Road Initiative. This makes it the most essential port in the international sea route. Built to conquer distance and defy gravity, the biggest bridges in the United States are colossal structures that push engineering to its limits. From coast to coast, these massive giants carry millions across rivers and city skylines every day. Today we'll explore the biggest bridges in the United States, uncovering the mind-blowing scale and power behind the nation's most iconic crossings. Let's travel over to the new Mississippi River Bridge, a crucial project that connects St. Louis, Missouri, and southwestern Illinois over the mighty Mississippi River. This massive bridge, officially named the Stan Musial Veterans Memorial Bridge, was designed to ease congestion on the existing Poplar Street Bridge, which was struggling to handle traffic volumes. The significance of this bridge goes beyond traffic relief. It plays a major role in boosting regional connectivity and economic development. By linking Interstate 70 across the Mississippi River, the bridge creates a more direct route for freight, commercial trucking, and cross-country travel. For the logistics and shipping industries, this new path cuts fuel costs, time, and congestion, making it an invaluable asset in the national transportation grid. Designed as a cable-stayed bridge, the structure features 2 massive towers inclined at 9 degrees from the river, with a main channel span of 2,000 feet and a total bridge length of 3,150 feet. These towers were carefully designed to eliminate obstructions to river traffic, especially for large cargo vessels that frequently navigate the Mississippi. Its 222-foot wide deck makes it the widest cable-stayed bridge in the world, carrying 8 full traffic lanes, 4 in each direction, plus 2 full shoulders, across the river. With such an expansive structure, the bridge required meticulous seismic engineering due to its location within the new Madrid seismic zone, one of the most active earthquake zones in the United States. Advanced internal mechanisms were integrated into the design to redistribute seismic stresses, ensuring stability in the event of an earthquake. This $700 million megaproject involved Modjeski and Masters as the primary design firm, handling both preliminary and final bridge designs. The construction called for more than 9,000 tons of steel, 2,100 miles of high-tension cables, and a foundation supported by deep drilled shafts and reinforced concrete. This endures the immense pressure from vehicle loads and environmental factors like river flooding. Massive cranes were employed to lift precast concrete segments into place for the tower and deck construction, while specialized equipment handled cable installation, anchoring, and tensioning. Heavy-duty floating cranes, GPS-guided pile drivers, and temporary cofferdams were among the advanced machinery and techniques used to build the bridge. Precast concrete segments were hoisted and locked into place, forming the deck and tower structures piece by piece. The team also applied post-tensioning techniques to ensure long-term flexibility and durability. Completed and open to traffic in 2014, the bridge now serves tens of thousands of vehicles daily, significantly reducing travel time between Missouri and Illinois. Next up, but we have to talk about the D-Line extension, a transformative $9.5 billion metro rail project expanding the subway system in Los Angeles. This massive project will extend the D-Line, formerly known as the Purple Line, significantly improving public transit across one of the most congested cities in the United States. With Los Angeles preparing for the 2028 Olympics, this metro extension is crucial in alleviating gridlock and modernizing the public transport infrastructure of the city. The idea of extending the subway system westward in Los Angeles has been in discussion since the 1980s. Initial plans envisioned a subway that would stretch all the way to Santa Monica, commonly referred to as the subway to the sea. However, due to funding constraints, the project was broken down into multiple sections, with the current expansion terminating at the Westwood Station. In 2010, Metro completed the draft environmental impact study, paving the way for an official decision in 2012 to move forward with construction. The first section of construction began in 2014, with additional phases following in 2017 and 2021. The final phase of tunneling was completed in April 2024, bringing the project one step closer to completion. The D-Line extension is a game changer for Los Angeles, promising to reduce traffic congestion on the notoriously gridlocked Wilshire Boulevard corridor. It will improve air quality by promoting public transit over car travel. This megaproject is expected to significantly cut travel times, making it possible to commute between Koreatown and Westwood in just 25 minutes, half the time it takes by car. The D-Line extension adds nearly 9 miles of underground tunnels, extending service from Wilshire in Koreatown to VA Hospital. The construction is divided into 3 major sections, each with a distinct timeline and set of stations. Section 1 extends from Weston to La Cienega, adding La Brea, Fairfax, and La Cienega stations. Section 2 will complete in 2026, extending to Rodeo and Century City. Section 3 will be completed in 2027, adding University of California and VA hospital stations. The project involves extensive underground excavation and tunneling beneath some of busiest streets in Los Angeles, which has presented unique engineering challenges. Tunnel boring machines have been deployed to carve out tunnels through the dense clay and sandy soil of the city. Given the earthquake-prone geography of the city, the subway is being reinforced with high-strength, seismic-resistant materials to withstand earthquakes and soil shifts. In April 2024, tunneling for the entire project was finished, marking a major milestone. Stations are now undergoing final construction and track installation. The first segment is set to open by the end of 2025, followed by additional sections in 2026 and 2027. Discussions continue about a fourth phase that could extend the D-Line another 3.5 miles to Santa Monica. This addition would connect the subway directly to the beach and the Expo line, further integrating the local rail network. The Los Angeles River Revitalization Taylor Yard G2 project is one of the most ambitious urban restoration efforts underway in the city, aiming to reconnect communities, ecosystems, and public space along a key stretch of the LA River. Located just northeast of downtown Los Angeles, the 42-acre, G2 parcel at Taylor Yard is a former rail yard with a deeply industrial past. Now, it's being transformed into a dynamic riverfront park with ecological restoration, public access, and flood resilience at its core. This high-profile project is progressing in phases with major construction milestones planned through 2025. Engineering the transformation of Taylor Yard. G2 begins with addressing its legacy as a contaminated brownfield site. Historically operated by Union Pacific Railroad, the land was used for train maintenance and freight operations, leaving behind petroleum byproducts, heavy metals, and solvents in the soil. Remediation efforts have involved large-scale soil excavation, on-site containment strategies, and installation of monitoring wells. Engineers have had to carefully remove contaminated soil while maintaining the structural integrity of nearby flood control infrastructure and not disturbing underground utilities running through the site. A defining feature of the project is the planned restoration of a naturalized riverbank along the LA River's concrete line channel. This involves regrading the shoreline to introduce terraced wetland zones that can absorb floodwater, support native vegetation, and create habitat for wildlife. To do this, engineers are selectively removing sections of the concrete river bottom and replacing them with engineered earth berms, riprap, and bioretention cells. These features are reinforced with geotextiles and planting beds that help stabilize the soil while supporting long-term ecological recovery. A new pedestrian and bike bridge, the Paseo del Rio, is also under construction. Linking Taylor Yard G2 with the adjacent Rio de Los Angeles State Park. The bridge is a steel truss structure designed for minimal impact on the river channel below, with deep concrete foundations set back from the banks. Prefabricated in sections off-site, the bridge is being assembled using temporary supports and will be craned into place once the piers are complete. The site will eventually include multi-use trails, interpretive features, and public gathering spaces shaded by drought-tolerant landscaping. Stormwater management is integrated throughout, using permeable pavement, bioswales, and underground filtration systems to treat runoff before it enters the river. Portions of the site will also retain the industrial legacy through adaptive reuse. Old rail structures and materials are being preserved and incorporated into public art and educational installations. Amid the expansive high desert plains of northern Arizona, the construction of the West Camp Wind Farm emerged as a strategic investment in renewable energy infrastructure. Spanning thousands of acres of open terrain, the project was meticulously engineered to optimize wind capture while minimizing environmental disruption and maximizing grid integration efficiency. The undertaking required a deep coordination of civil, electrical, and structural disciplines, especially given the logistical challenges of transporting and installing massive turbine components in a remote landscape. Site preparation began with extensive meteorological analysis, which had been ongoing for several years using temporary meteorological towers. Data from these towers informed turbine placement by mapping wind patterns, speeds, and turbulence intensity across the site. Once the final layout was approved, access roads were constructed to facilitate the movement of heavy equipment. These roads, typically graded gravel with a geotextile base layer, were designed to handle repeated loads from cranes, trucks, and transport trailers carrying nacelles, blades, and tower segments. Foundation work for each wind turbine involved excavation of large circular pits, generally more than 60 feet in diameter and over 10 feet deep. Soil conditions varied across the site, requiring a combination of mass concrete footings and rock-anchored base plates. After forming and rebar cage placement, concrete was poured and cured under controlled conditions to prevent thermal cracking. Anchor bolt assemblies, precisely set to tight tolerances, were embedded within the foundations to receive the tower base flange. Delivery of turbine components to the site was a carefully orchestrated operation involving specialized transport vehicles and often required temporary modifications to public roads and intersections. Each turbine consisted of multiple tower sections, a nacelle housing the generator and gearbox, and 3 blades, often exceeding 150 feet in length. Staging areas were created near each foundation to store components in sequence prior to assembly. Erection of the wind turbines was carried out using high-capacity crawler cranes and assist cranes. The process began with vertical assembly of the tower sections, lifted and bolted sequentially from base to hub height. Crews worked at height using safety harnesses and enclosed platforms. Once the nacelle was lifted into place and secured, the rotor assembly was completed either on the ground and hoisted in a single lift, or blade by blade, depending on wind conditions and crane capacity. Electrical infrastructure was developed in tandem with turbine installation. Each turbine was connected via underground medium voltage cables to pad-mounted transformers, which stepped up voltage for transmission to a central substation. The substation, constructed on a separately graded pad, featured power transformers, circuit breakers, protection relays, and SCADA systems to monitor and control generation output. From there, power was transmitted to the regional grid via a newly constructed overhead transmission line connected to the nearest utility intertie point. Environmental compliance remained a critical aspect throughout construction. Dust control measures, wildlife monitoring, and erosion control systems were maintained, especially during foundation excavation and road grading. Upon completion, disturbed areas were regraded and reseeded with native vegetation to restore habitat. In the rapidly developing entertainment corridor near Glendale, Arizona, the construction of Mattel Adventure Park introduced a highly specialized category of themed development that combines amusement rides with immersive retail and branded environments. This hybrid entertainment venue required a unique convergence of architectural theming, structural engineering for amusement ride systems, and complex mechanical integration to support both indoor and outdoor attractions under Arizona's harsh desert climate. Groundbreaking began with extensive grading and subgrade stabilization as the site demanded precise elevation control to accommodate a mixture of flat ride pads, roller coaster foundations, utility corridors, and pedestrian pathways. Because large sections of the park are enclosed or partially shaded, the foundation systems were designed not only for structural support, but also to accommodate below-slab MEP systems, such as drainage piping, chilled water lines, and conduit for low-voltage systems. A primary engineering focus was the integration of steel-framed ride support systems with the park's architectural envelope. Roller coasters and track-based rides required deep pile foundations and custom fabricated support columns anchored using precision survey controls. Load paths from dynamic forces were modeled using structural analysis software to ensure stability under varying operational and seismic conditions. Coordination between ride manufacturers and local structural engineers was critical to ensure the embedded hardware matched with the prefabricated ride sections delivered to the site. Indoor areas of the park were enclosed with high bay pre-engineered steel buildings, clad in themed architectural facades composed of metal panels, EIFS systems, and specialty coatings to match Mattel's brand aesthetics. HVAC systems for the enclosed attractions were robust, with rooftop air handling units and large ductwork plenum systems distributing conditioned air to maintain interior climate control for both guests and sensitive ride equipment. Utility demands were substantial. Electrical loads included lighting, sound systems, ride controls, food service operations, and administrative zones. A central utility corridor distributed high-capacity power, fiber optics, and water mains throughout the park. Mechanical and electrical rooms were located beneath platform structures and within service corridors, ensuring discrete access for maintenance without interrupting guest flow. Safety and access compliance were integrated from the outset. All platforms, queuing areas, and emergency egress paths were constructed in accordance with amusement ride codes and ADA guidelines. Queue lines were designed with both shade structures and interactive theming elements, requiring coordination between landscape designers, structural engineers, and scenic fabricators. The construction of Mattel Adventure Park ultimately combined the disciplines of industrial ride engineering and commercial construction with creative theming, delivering a facility that supports high daily throughput while withstanding the operational and environmental rigors of the Arizona desert. Phoenix Sky Harbor, International Airport, often called America's friendliest airport, is not just a critical hub for travelers across the Southwest. It's a sprawling, complex system of aviation, civil, and structural engineering designed to handle over 40 million passengers annually. Located in the heart of Phoenix, this airport's infrastructure must meet extreme operational demands while contending with the punishing desert climate, high air traffic volume, and continuous expansion requirements. Sky Harbor's airside and landside components are both engineered to the highest levels of precision. The airfield includes 3 parallel runways, with the longest stretching over 11,000 feet to accommodate fully loaded, wide-body aircraft, particularly during the hot summer months when thinner air reduces lift. These runways are built with multiple layers of high-strength Portland cement concrete, engineered with dowel bars and expansion joints to manage thermal cycling and prevent surface cracking. Below the pavement, advanced drainage systems channel rainwater from the rare but intense desert storms into underground retention basins. Taxiways and aprons are carefully configured for maximum throughput. The airport uses a system of dual and triple parallel taxiways that reduce aircraft taxi time and minimize runway occupancy. Edge lighting, in-pavement lighting, and a network of instrument landing systems allow for 24/7 operations, even under low visibility. At the terminal level, engineering complexity intensifies. Terminals 3 and 4, the busiest, are built with massive steel and concrete frames capable of withstanding seismic forces, high winds, and the heavy dynamic loads of passenger crowds and baggage systems. Vertical circulation cores include escalators, elevators, and stairways designed to move thousands of people per hour, especially during peak travel times. Terminal 4 alone includes over 90 gates, each with its own passenger boarding bridge, supported by power, HVAC, and data systems to connect to aircraft systems during turnaround. Beneath the terminals is a vast network of baggage handling systems, utilizing miles of conveyor belts, diverters, RFID tracking sensors, and automated sorters. These systems are not only engineered for high-speed efficiency, but also maintain strict TSA security protocols, including inline explosive detection systems embedded within the conveyor routes. Another engineering feat is the PHX SkyTrain, a fully automated people mover that links terminals with parking, rental car centers, and the Valley Metro Light Rail. The elevated concrete guideway was constructed using segmental bridge techniques, with precast segments post-tensioned together and supported by piers spaced to avoid disrupting existing roadways and taxi lanes. The trains themselves are electrically powered, with embedded induction systems for regenerative braking and energy recovery. Mechanical systems across the airport are engineered with redundancy and resilience. Chilled water systems cool millions of square feet of terminal space, backed by central utility plants with backup generators and advanced control systems that respond to variable occupancy loads. Roof structures are equipped with reflective membranes and radiant barriers to reduce heat absorption, critical for maintaining energy efficiency in the desert climate. All of this is tied together with an advanced air traffic control tower, the tallest in Arizona, equipped with radar, weather monitoring, and communication systems that coordinate hundreds of daily arrivals and departures with millisecond precision. It's time to move over to Saudi Arabia for the Red Sea Global Project. The investment for this development stands at an astonishing $17 billion. The project is going to create world-class destinations along Saudi Arabia's pristine west coast while championing regenerative tourism, working on improving the environment rather than sustaining it. So, what is Red Sea Global? Imagine 28,000 square kilometers as a tourism resort, bigger than many countries. It is situated between Saudi cities Lujj and Al Waj, which will be one of the biggest investments in the region, with 50 luxury resorts, 8,000 hotel rooms, and over 1,000 residences. These aren't your regular beachfront hotels. They'll be built with the surroundings incorporated into them, including lush island retreats, desert hideaways, and many more. For example, luxury marinas, golf courses, and so many others are going to be customized to entertain travel lovers, who, if they want a mix of both adventure and rest, will also find it at Red Sea Global. While this is the reduction of harm toward nature, what is even more important is to restore and make it even better. As an example, the project centers around the safeguarding of the world's healthiest and most biodiverse coral reefs in the Red Sea. To date, 95% of the biodiversity will not be touched at all, and marine life coexists with the human development process. Innovative measures, including marine spatial planning, ensure that the activities of construction and tourism are conducted with the least impact on ecosystems. One of the greatest features of Red Sea Global is the heavy stress they put on sustainability. They house the largest solar farm worldwide, which therefore has enabled the project to be powered wholly by renewable energy. Unlike many traditional destinations fueled by fossils, Red Sea Global is an off-grid destination relying on solar, wind power, and battery storage for all the needed energy there. The infrastructure is built according to LEED gold standards and focuses on energy efficiency, water conservation, and the use of sustainable materials. Even logistics and construction are based on this principle, and all of the distribution centers are designed with a minimal carbon footprint. This progress so far is indeed nothing short of remarkable. Scores of resorts have been built, and an international airport has also been constructed. For convenience and its seamless connectivity to travelers, the international airport itself, evidence of the project's focus on sustainability, stands out with great efficiency in terms of energy use from its design and operations. Red Sea Global has also embraced sustainable supply chain practices, getting a good percentage of materials locally sourced, and indeed, avoiding massive waste by beautiful methods of recycling. Looking toward the future, one of the most intriguing aspects of Red Sea Global is its goal to go beyond tourism and become a model of how large-scale development can coexist with the environment. Initiatives include coral reef nurseries, which are already showing significant results, and the establishment of marine sanctuaries to protect and study aquatic biodiversity. The project's education and research centers are intended to contribute to global discussions on sustainable practices. This dual focus on development and environmental stewardship ensures that Red Sea Global will not only provide immediate economic benefits, but also serve as an example of how tourism can be a force for environmental good. The Red Sea Global project is not just a development, but a transformative vision for tourism and environmental harmony. Spanning an area equivalent to a small country, it integrates luxury tourism with ecological preservation in an unprecedented way. For instance, the project emphasizes preserving the delicate marine ecosystems of the Red Sea. Advanced coral propagation techniques are being employed to restore degraded reefs and ensure the biodiversity of marine life thrives alongside tourism activities. Visitors can witness marine life in its natural habitat through carefully planned, low-impact diving and snorkeling experiences, which promote conservation awareness. Additionally, the architectural designs of resorts and facilities blend seamlessly with their surroundings. From island-inspired retreats that mimic natural landscapes to desert lodges reflecting traditional Bedouin aesthetics, every element focuses on sustainable living. Each building uses innovative materials to minimize environmental impact and incorporates renewable energy technologies, such as solar panels and wind turbines, into its infrastructure. The Red Sea Global project also aims to redefine luxury travel by introducing personalized, environmentally conscious experiences. Guests will have access to activities like guided eco-tours, marine biology workshops, and cultural programs that celebrate the heritage of the region. Moreover, initiatives like water desalination plants, powered by renewable energy, and waste recycling systems set new standards for sustainable resource management in tourism. By incorporating a mix of development, conservation, and community involvement, Red Sea Global serves as a blueprint for the future of regenerative tourism. It goes beyond just maintaining the environment. It actively seeks to improve and replenish natural habitats while creating economic opportunities for local communities. This visionary project is poised to make a global impact, offering a sustainable model that combines luxury with responsibility. Let's travel over to the Vincent Thomas Bridge rehabilitation, a $600 million upgrade to one of the busiest port bridges in California. Spanning over the Los Angeles harbor, the bridge connects San Pedro to Terminal Island, serving as a vital transportation route for commercial and commuter traffic. With growing trade and increasing seismic risk in California, the need for structural reinforcement and modernization of the bridge has become urgent. The Vincent Thomas Bridge was originally completed in 1963, named after Vincent Thomas, a California assemblyman who fought for decades to secure funding for the project. At the time, it was the first welded suspension bridge in the United States and a major engineering achievement. It provided a much-needed direct connection between booming port facilities in Los Angeles and the rest of the city. Over the years, the bridge has become a critical artery for trade, carrying thousands of trucks daily, many of them transporting goods from the Port of Los Angeles, one of the busiest ports in the world. However, decades of wear and tear, increased traffic, and frequent seismic activity in California have put tremendous strain on the bridge, necessitating an extensive rehabilitation project. The rehabilitation project is designed to ensure the long-term stability of the bridge, enhance safety standards, and reduce maintenance costs. One of the most crucial aspects of the upgrade is seismic retrofitting, which will allow the bridge to withstand major earthquakes, a significant threat in the earthquake-prone region of Southern California. Engineers are reinforcing the main towers and foundations of the bridge, installing steel dampers and flexible expansion joints that can absorb seismic shock. In addition to seismic improvements, the project will focus on expanding traffic lanes and modernizing roadway surfaces. The goal is to increase traffic flow efficiency, reducing congestion and delays, particularly for commercial trucks that depend on this route. Steel cable reinforcements will be installed along the suspension system to prevent corrosion and extend the operational lifespan of the bridge. The budget for the project has been set at $600 million, with funding coming from state and federal infrastructure programs. Given the strategic importance of the bridge to the economy of Los Angeles, significant investments have been made to ensure its structural integrity and operational efficiency. Construction crews are utilizing advanced crane operations to maneuver large steel components into place. Heavy-duty drilling equipment is being used to strengthen the foundations of the bridge, ensuring that it remains structurally sound for at least another century. High-precision welding technology is being employed to repair and reinforce key sections of the suspension cables and road decking. Currently, the Vincent Thomas Bridge rehabilitation is progressing steadily, with completion expected in 2026. The LAX Landside Access Modernization Program, often referred to as LAMP, is one of the most transformative infrastructure projects currently underway at any airport in the United States. Focused on reimagining how passengers access Los Angeles International Airport, the project involves an extensive network of new roadways, intermodal facilities, and an automated people mover system that will completely overhaul the travel experience. With completion expected in 2025, LAMP is reshaping how millions move through one of the world's busiest airports. At the center of the project is the Automated People Mover, a 2.25-mile elevated train system designed to connect terminals with new parking structures, a consolidated rental car facility, and a new transit hub called the Intermodal Transportation Facility West. The guideway is being constructed using large precast concrete segments, which are fabricated off-site and then transported and lifted into place using segmental launching gantries and cranes. This method minimizes the need for extensive on-site formwork and reduces interference with the airport's active operations. Each station along the People Mover route is being built with high-strength concrete foundations and steel superstructures. The platform areas incorporate anti-vibration and noise mitigation technologies, including floating slab track beds and sound-absorbing panels. Glass curtain walls and open-air designs enhance natural lighting and airflow while maintaining strict security and access control. Another major component of the program is the Consolidated Rent-a-Car Facility. This is a massive structure spanning over 6 million square feet, designed to house over 18 rental car companies in one centralized location. Structurally, the Conrack features long-span concrete decks, post-tension slabs, and a complex vertical circulation system of ramps and elevators engineered to handle thousands of vehicles per day. On the ground level, a smart traffic flow system is being integrated, using sensors and digital signage to guide vehicles efficiently through drop-off and pickup zones. The project also includes a complete overhaul of the roadways leading into and out of the airport. This involves widening lanes, adding dedicated busways, and building new flyovers that separate private vehicle traffic from commercial shuttles and transit services. These improvements require deep excavations, extensive utility relocations, and the installation of new stormwater drainage systems. Coordinating all this work while keeping the airport fully operational demands a high level of precision in scheduling and logistics. Construction teams are working around the clock, often at night, to reduce disruption. When finished in 2025, LAMP will make LAX far more accessible, sustainable, and efficient for decades to come. In the western reaches of the Phoenix metropolitan area, the construction of Buc-ee's in Goodyear, Arizona, introduced a uniquely large-scale convenience and fueling center to the southwest. Known nationally for its sprawling facilities and extensive amenities, building a Buc-ee's location required coordination across civil, structural, mechanical, and traffic engineering disciplines. The Goodyear site posed specific challenges related to site access, utility capacity, and the sheer size of the development, which spans tens of thousands of square feet under roof and includes well over 100 fuel pumps. Construction began with site acquisition and preparation on a parcel of land located near a high-traffic interstate interchange. Grading and earthwork were extensive, as the natural topography included uneven terrain and drainage channels that needed to be recontoured. Bulldozers and graders worked in tandem with GPS-guided systems to establish flat pads for the main building, fuel canopy, and ancillary structures, while engineered fills and retention basins were shaped to manage stormwater runoff and comply with local drainage ordinances. Installation of utilities was an early priority. Buc-ee's facilities demand significant electrical and water service to support lighting, refrigeration, HVAC, restrooms, car wash systems, and commercial kitchen operations. Multiple utility corridors were trenched and installed in parallel, with electrical conduits, sewer mains, and domestic water lines placed in pre-engineered routes. Electrical service included pad-mounted transformers and switchgear designed to handle peak loads with backup circuits for critical systems. A dedicated fire suppression loop with underground hydrants and backflow prevention was installed to serve both the retail building and fueling areas. The main structure was constructed using a combination of steel framing and reinforced masonry. Structural steel columns and open web joists form the building's skeleton, supporting a metal roof deck over which rigid insulation and membrane roofing were applied. Masonry walls, reinforced with vertical rebar and grout-filled cores, provided lateral stability and durability against thermal expansion in the desert climate. High-performance glazing and insulation systems were used to meet energy codes and reduce cooling loads in the expansive interior. Fueling infrastructure represented a major component of the build. Underground storage tanks were installed in concrete-lined excavations with leak detection and vapor recovery systems. These tanks, some with capacities exceeding 30,000 gallons, required anchoring systems to prevent flotation due to potential groundwater intrusion. Fuel lines were routed from the tanks to the dispensing stations using flexible double-walled piping encased in protective sleeves. Above each fueling island, the steel canopy was erected with integrated lighting, signage, and fire suppression nozzles. Interior build-out included extensive plumbing, food service equipment installation, and climate control systems. The building's layout was optimized for high customer throughput, with wide aisles, durable epoxy flooring, and stainless steel fixtures. HVAC systems were zoned and included large rooftop units controlled by a centralized building automation system to maintain efficiency. Finally, site access improvements were constructed, including new turn lanes, deceleration lanes, and signalized intersections to manage the high volumes of passenger and delivery vehicle traffic. Parking lots and access roads were paved with reinforced concrete in high traffic areas and asphalt in general zones. The Buc-ee's Goodyear project demonstrated how meticulous planning and large-scale construction techniques come together to create a retail destination engineered for efficiency, resilience, and customer capacity. The Mike O'Callaghan Pat Tillman Memorial Bridge is one of the most iconic and technically advanced arch bridges in the United States. Spanning 1,900 feet across the Black Canyon between Arizona and Nevada, just downstream from the Hoover Dam, this massive concrete steel hybrid structure was designed to carry US Route 93 high above the Colorado River, while solving a long-standing traffic and safety issue along the winding dam road. Structurally, the centerpiece of the bridge is its 1,060-foot twin-rib concrete arch, the longest of its kind in North America. This arch supports a deck that sits 890 feet above the river, making the bridge the second highest in the United States. Building such a span in a location with steep canyon walls, high winds, and limited access demanded not only innovative design, but also extreme precision in execution. The foundation work began with drilling massive concrete footings directly into the canyon's rock walls. Engineers had to contend with fractured volcanic rock, which required extensive grouting and anchoring to create stable load paths. Each arch rib rests on bearings set into these foundation blocks, and from there, the ribs rise in parallel curves, eventually meeting at the center of the span with a keystone closure that locked the entire system into compression. One of the most extraordinary aspects of the bridge's construction was how the arch itself was built. Crews used a cantilever method, building the arch outward from both sides of the canyon simultaneously using temporary cable-stayed towers anchored high on the cliffs. These towers supported the growing arch segments with steel cables. Adjusted daily, to counteract wind loads, thermal expansion, and minute misalignments. Surveying teams used laser-guided systems accurate to within millimeters to ensure both halves of the arch met perfectly in the middle. Once the arch was closed and self-supporting, the construction of the deck began. The bridge deck is a composite system made of cast-in-place, reinforced concrete supported by steel box girders that span between vertical spandrel columns rising from the arch. These columns are designed with ductility in mind, allowing slight movement in the event of seismic activity. The entire structure is engineered to withstand extreme temperature fluctuations, high winds, and the seismic risks posed by the region. Expansion joints and bearings at the abutments accommodate movements in the bridge due to thermal cycling, while wind tunnel testing informed the aerodynamic profile of the deck and parapets to ensure long-term stability. Aesthetically, the bridge complements the nearby Hoover Dam without overshadowing it. The clean, minimalist lines of the arch and deck frame the landscape, while the materials, light-toned concrete and weathered steel, blend subtly with the surrounding canyon walls. Pedestrian access is also included, with a walkway that offers sweeping views of the dam and river below. But how about Colombo Port City, located in Sri Lanka? Built on $1.4 billion worth of reclaimed land, this mega development is set to become an international financial and business hub, attracting global investors with tax incentives and modern infrastructure. But as impressive as it sounds, it's not without its controversies. The vision behind Colombo Port City is nothing short of transformative. Located along the seafront of Sri Lanka's bustling capital, Colombo, this project aims to create a state-of-the-art urban space with financial districts, residential areas, luxury marinas, and green parks. The city is designed to position Sri Lanka as a regional economic powerhouse, offering tax holidays and financial incentives to attract multinational corporations and international banks. The hope is that it will bring in billions of dollars in foreign investment, create thousands of jobs, and establish Sri Lanka as a key player in the global economy. The scale of the project is staggering. Covering 665 acres of land reclaimed from the Indian Ocean, Colombo Port City is often compared to the rapid urban development seen in places like Dubai and Hong Kong. Its planners envision an offshore financial center where all transactions, including salaries, will be conducted in US dollars, creating a business-friendly environment. The city's layout includes residential zones, commercial hubs, and even a marina to cater to luxury yachts. While the project presents such a gigantic promise, it did not happen without its challenges and concerns. The most significant one has to do with funding and execution. The reclamation of the land and initial work were financed by China Harbour Engineering Company, which is under China Communications Construction Company. It reportedly invested $1.4 billion in return for a 43% share in a 99-year leasehold. This heavy involvement from China has raised fears that Colombo Port City could become a Chinese enclave within Sri Lanka. Critics fear the long-term implications of such an arrangement, with some raising concerns about sovereignty and the potential for Chinese economic dominance in the region. These fears aren't entirely unfounded though. Sri Lanka has already experienced difficulties with Chinese-funded projects, like the highly contested Hambantota port, which Sri Lanka was forced to lease to China after failing to pay off its loans. Environmental concerns are another issue that people have raised. Reclamations taken from the sea largely changed the dynamics of the existing ecosystem. Others argue that no proper analysis took place while devising this. Another thing in question is the financial benefits to Sri Lanka from such a venture, the tax holidays, etc. And a lot more is being thought of in terms of restraining the project's influence towards the nation. about the John James Audubon Bridge, the longest cable-stayed bridge in Louisiana. Completed in May 2011, this colossal cable-stayed structure stretches across the Mississippi River, linking Point Coupe Parish and West Feliciana Parish in Louisiana. John James Audubon Bridge is the longest cable-stayed bridge in Louisiana and the second longest main span in the Western Hemisphere, measuring 1,583 feet between towers. With a total bridge length of 12,883 feet, it surpasses many of its global counterparts and plays a vital role in transforming regional infrastructure. Before the Audubon Bridge existed, residents and vehicles had to rely on a century-old ferry system to travel between New Roads and St. Francisville. The ferry, while iconic, was often slow, subject to weather delays, and unable to meet the region's growing transportation needs. The bridge now serves as the only river crossing for nearly 90 miles between Natchez, Mississippi, and Baton Rouge, Louisiana. This makes it a critical transportation lifeline along the Louisiana Highway 10 corridor and the Zachary Taylor Parkway. The Audubon Bridge was designed to accommodate 4 lanes of traffic, with 2 11-foot travel lanes in each direction, plus outside and inside shoulders. It provides 2.44 miles of elevated roadway, seamlessly connecting to 12 miles of newly constructed 2-lane roads and linking LA 1 to US 61 through 4 major intersections. From a construction standpoint, the bridge was a massive endeavor, with a total budget of $409 million. The structure incorporates reinforced concrete piers, high-tension stay cables, and hydraulic lifting systems. One particularly unique feature is the use of 24-ton finger-type sliding joints that allow for deck movements up to 49 inches. These joints were critical for managing the flexibility of this colossal structure in response to thermal expansion, river current, and wind loads. The bridge became fully connected across the river by December 29, 2010, but due to flooding and the forced closure of the ferry, it was open to the public earlier than scheduled on May 5, 2011. Since then, it has improved regional connectivity, reduced travel times, and significantly boosted the economic flow between both parishes. Culturally, the name of the bridge pays homage to John James Audubon, the renowned artist and naturalist who spent part of 1821 in St. Francisville. Audubon painted several pieces from his famous Birds of America series. While some lawmakers later proposed renaming the bridge after military generals native to the region, yet a compromise was reached in favor of the famous painter. Hollywood Park Development, a transformational $5 billion mixed-use mega project that is redefining Inglewood, California into a world-class entertainment district. Situated on a 298-acre site, this massive development is one of the largest real estate projects in the United States. The centerpiece of Hollywood Park is SoFi Stadium, a state-of-the-art sports venue that is home to both the Los Angeles Rams and the Los Angeles Chargers. Opened in 2020, it is the most expensive NFL stadium ever built, featuring a massive 70,000 seat capacity, a translucent roof, and digital technology, including a 4K dual-sided Oculus video board. SoFi Stadium has already hosted Super Bowl LVI in 2022 and will be a central venue for the 2028 Summer Olympics in Los Angeles. Beyond the stadium, Hollywood Park is designed as a vibrant entertainment hub. The YouTube Theater, an intimate 6,000-seat performing arts venue, is attracting major concerts, award shows, and live events. Hollywood Park Casino, an upgraded gaming and leisure destination, further enhances the entertainment offerings of this place. A 25-acre public park, an artificial lake, and open green spaces offer scenic landscapes and recreational areas for residents and guests. Building Hollywood Park required complex engineering and large-scale construction techniques. The stadium excavation alone removed over 6 million cubic yards of soil, requiring the largest urban excavation project in US history. Due to its proximity to Los Angeles International Airport, The stadium's height was restricted, necessitating a below-ground playing field 100 feet below street level. To support the structures, developers used advanced seismic engineering to ensure earthquake resilience. Construction has also involved high-tech machinery, including tower cranes, massive earth movers, and advanced steel-reinforced concrete to ensure the longevity and durability of the development. The stadium roof, a complex ethylene tetrafluoroethylene material, is a lightweight yet durable structure, allowing natural light to filter in while protecting visitors from extreme weather. Hollywood Park is still evolving, with ongoing construction of new residential complexes, office spaces, and additional entertainment venues. The completion of the entire project is expected by 2026, marking one of the most significant urban transformations in the history of California. The Chase Center development in San Francisco is much more than just an arena. It's a full-scale urban redevelopment project that transformed a formerly industrial stretch of the Mission Bay neighborhood into a world-class sports and entertainment hub. Anchored by the state-of-the-art Chase Center Arena, the home of the Golden State Warriors, the project also includes 2 office towers, a sprawling public plaza, retail spaces, and major transportation upgrades. While the arena officially opened in 2019, surrounding infrastructure, streetscape, and commercial components have continued to evolve, with final phases completing through 2025. The heart of the development is the 18,000-seat Chase Center itself, designed to accommodate not just NBA games, but concerts, conferences, and cultural events. Structurally, the arena was built using a massive concrete and steel frame with a unique oval footprint. The foundation required excavation down to bedrock, with deep concrete piles and a mat slab anchoring the structure for seismic resilience. Given San Francisco's proximity to active fault lines, seismic engineering was a critical priority. The entire structure is designed with base isolators, large rubber and steel bearings that allow the building to move independently from the ground during an earthquake, significantly reducing structural stress. Above ground, the bowl-shaped arena features long-span roof trusses made from structural steel, some over 300 feet in length, which were assembled on-site and hoisted into position using synchronized crane lifts. The roof supports a large central scoreboard, extensive lighting rigs, and a distributed load of rigging for concerts and events. The exterior skin combines glass, metal panels, and architectural fins that wrap the building in a sleek, modern envelope. Flanking the arena are 2 11-story office towers, developed in partnership with Uber. These buildings use a concrete core and steel frame construction, clad in reflective glass curtain walls. Their design integrates with the arena through elevated walkways and shared podium levels that contain retail, restaurants, and back-of-house functions. Beneath the development, a vast underground parking garage accommodates thousands of vehicles with separate service docks to manage event day logistics without disrupting pedestrian movement. One of the most impressive components is Thrive City, the open-air plaza and public space that serves as the development's civic heart. Constructed with post-tensioned concrete slabs and detailed landscape architecture, this area hosts watch parties, farmers markets, and fitness events. Integrated lighting, stormwater treatment systems, and large digital displays make it both functional and dynamic. Finally, the project required major upgrades to local infrastructure. New Muni Light rail platforms were built adjacent to the site, roadways were realigned, and bike and pedestrian pathways were added to support car-free access. Utility systems, including electrical, water, data, and sewer, were upgraded and rerouted in coordination with city agencies, all while maintaining service continuity to neighboring medical and academic campuses. Tucked within the expanding industrial corridors of the Phoenix metropolitan area, the development of Mack Innovation Park marks a significant addition to Arizona's logistics and advanced manufacturing infrastructure. Conceived as a high-capacity, master-planned industrial complex, this project demanded extensive land preparation, high-performance building construction, and strategic utility coordination to accommodate a range of high-tech tenants and warehousing operations. The entire endeavor had to balance rapid deployment schedules with strict technical and environmental requirements, especially given the scale of build-out across hundreds of acres. Initial groundwork began with site clearing, grading, and soil stabilization. Given the arid climate and typically sandy soils of the region, crews employed compaction and cement-treated base layers to ensure stable subgrades. Laser-guided grading equipment shaped the landscape according to precise elevation tolerances, enabling future buildings to maintain proper drainage and prevent settlement. In areas with expansive clays or other problematic soils, lime treatment was used to improve load-bearing capacity and minimize heave potential. Utility installation came next and involved major trenching operations to lay out an underground network for stormwater, sewer, potable water, reclaimed water, and fire suppression systems. Due to the park's high energy demand projections, the electrical infrastructure included large-scale conduit banks and dual-feed substations designed to deliver redundancy and reliability. Telecommunications infrastructure was also embedded at an early phase, with fiber optic backbones laid in parallel to power ducts to serve future tenants with high-speed connectivity. With infrastructure in place, building construction moved forward on multiple fronts, often with overlapping phases across the expansive site. The warehouse and advanced manufacturing structures typically featured tilt-up concrete panel walls, chosen for their speed of construction and cost efficiency. These panels were cast horizontally on-site, reinforced with steel rebar, and lifted into position using hydraulic cranes. After alignment and bracing, they were welded to embedded plates in the foundation and tied together with structural steel roof systems. Roof systems for these buildings incorporated long-span steel joists and mechanically fastened TPO membrane roofing, which offered durability and reflectivity in Arizona's intense sunlight. Several buildings included clear-story glazing and rooftop HVAC units mounted on steel platforms, allowing for flexible interior space configurations without ground-level obstructions. Interior fit-outs were designed to accommodate a wide range of tenant uses, from light manufacturing to distribution and research activities. This flexibility was achieved through wide column spacing, high clear heights, and heavy-duty floor slabs designed for forklift traffic and equipment loads. Electrical and mechanical systems were installed with scalability in mind, including transformer vaults, backup generator pads, and chilled water loops in select areas. Site development was completed with extensive truck courts, dock-high loading bays, and auto parking lots constructed of reinforced concrete and asphalt pavements. Landscaping used xeriscape principles, combining native desert plants with efficient drip irrigation systems to reduce water consumption. Site lighting utilized LED fixtures mounted on steel poles with photocell and motion control systems to reduce energy usage during off-peak hours. Mack Innovation Park stands as a prime example of contemporary industrial development tailored for versatility, efficiency, and rapid tenant deployment. The project reflects the growing demand for scalable, infrastructure-rich environments capable of supporting Arizona's evolving economic landscape. The Sunlink Street Car in Tucson, Arizona, is a compact yet technically sophisticated transit system that threads through the heart of the city, connecting the University of Arizona, downtown Tucson, and the Mercado district. At just under 4 miles long, it might seem modest in scope, but the engineering and construction behind it required surgical precision, deep utility coordination, and multimodal urban integration to bring modern street-level rail service into a historic and densely built environment. The foundation of the Sunlink system lies in its embedded track structure. Unlike elevated or segregated rail systems, Sunlink runs entirely at street level, sharing lanes with automobiles, bicycles, and pedestrians. This meant that the track slab had to be installed flush with the existing road surface, requiring extensive demolition, subgrade stabilization, and reconstruction of the roadway. Engineers excavated down to existing utility corridors, reconditioned the soil to reduce settlement risk, and installed new track-supporting slabs using reinforced concrete with embedded steel tie bars. A major engineering challenge involved underground utility relocation. Tucson's downtown core has aging infrastructure, water mains, sewer lines, storm drains, electrical conduits, and telecommunications. These had to be either replaced, lowered, or rerouted to prevent future conflicts with the rail system. Utility mapping was done with ground-penetrating radar, and construction often proceeded in short, block-by-block sections to maintain local access while minimizing service disruptions. The track itself uses grooved rail embedded into concrete, allowing for smooth vehicle passage across the trackway. Vibration isolation pads are placed beneath the rails to reduce noise and vibration transmission into nearby buildings, especially important along narrow streets lined with historic structures. These pads also help maintain track alignment in the face of Tucson's extreme temperature swings and potential soil movement. The overhead contact system, which powers the streetcars, was engineered to fit seamlessly into the streetscape. Steel poles are strategically placed to avoid visual clutter, often integrated into existing street lighting infrastructure. The catenary wires supply 750 volts of DC power, regulated through substations spaced along the alignment. These substations include transformers and switchgear housed in custom enclosures that blend with the urban fabric. The streetcars themselves are modern, low-floor vehicles with bidirectional operation, eliminating the need for turning loops. Each car is equipped with regenerative braking systems that reduce power demand and improve efficiency. Onboard systems are linked to a central operations center via a fiber optic network laid alongside the track, allowing real-time vehicle tracking, signal prioritization, and passenger information updates. Signal integration was a major piece of the engineering puzzle. The Sunlink system interfaces with city traffic signals through a transit signal priority system, allowing streetcars to maintain schedule reliability without overly disrupting vehicular flow. Signal heads and track switches are controlled via GPS and onboard vehicle logic units that communicate with the city's traffic management infrastructure. Finally, every station platform had to be precisely engineered for ADA compliance, ensuring level boarding with the streetcars. These platforms feature tactile paving, shade canopies, real-time arrival signage, and integration with pedestrian crosswalks and bike lanes. Since many stations are located on narrow streets, the design focused on compact, modular elements that could be installed with minimal disruption to surrounding businesses and foot traffic. It's time to travel over to Nusantara, the brand new capital of Indonesia. It's one of the most ambitious megaprojects going on today in the world. Just think about moving the entire government and millions of people from one of the most congested cities in the world, Jakarta, to a new sustainable city in the middle of Borneo. Today's capital, Jakarta, is sinking due to the weight of success. Overpopulation, coupled with acute traffic congestion and degradation of the environment, has worn it out to exhaustion. But that is not enough. Parts of Jakarta sink into the ground because it extracts too much groundwater, making the city all the more susceptible to flooding. There are more than 10 million living in this city within its boundaries. It cannot hold this pressure any longer. For this reason, Indonesia decided to take the very bold step to build Nusantara Green and Smart City that could start anew with these challenges facing it. Nusantara has been built to decentralize the economic activities so that regional economic growth can flourish without putting a greater burden on heavily populated Java, Indonesia's most populated island. Unlike the capital city Jakarta, Nusantara stands on higher land, making the new capital of Indonesia more susceptible to rising seas and climate shifts. The very name Nusantara reflects the unity of Indonesia's vast archipelago, so this is a symbolic choice for the nation's new capital. Progress on the project has already begun. The construction of the presidential palace has started, with great designs featuring modern architecture married to traditional Indonesian design. Great effort has been exerted in acquiring lands without placing a heavy burden on local communities and ensuring the inculcation of beauty within nature. The city will be anchored on renewable energy sources, as there are plans for the utilization of solar, wind, and hydropower to make Nusantara an eco-friendly capital. The issue of deforestation is a big challenge for the project. Environmental groups sound the alarm concerning how these fragile ecosystems might be badly damaged. A promise was issued by the government to implement measures toward protecting the environment, but again, the trick will be to balance between development and preservation. The cost is another important issue. It is estimated that the development of Nusantara will cost about $33 billion, which is a lot of money for a country that still has so many problems that are still very urgent, like poverty and healthcare. Critics say that this amount could have been used to solve other, more pressing problems or even enhance the infrastructure in the whole country. However, the government is still interested in the project and believes it to be a long-term investment in Indonesia's future. Let's move over to the Long Beach International Gateway Bridge, a modern engineering marvel replacing the Gerald Desmond Bridge in the busiest port of California. This enormous structure stands as the tallest bridge in Southern California, spanning a total of 8,800 feet and soaring above the busy port of Long Beach. This project was driven by necessity. The original Gerald Desmond Bridge, opened in 1968, had become outdated, structurally deficient, and too low to allow the tallest container ships in the world. With the port of Long Beach being one of the busiest shipping hubs in the country, the need for a high clearance replacement became urgent. Engineers designed the new bridge with a vertical clearance of 205 feet, providing uninterrupted access for the next generation of ultra-large vessels. Being the first cable-stayed bridge in California, the Long Beach International Gateway is also the only structure of its kind in the Los Angeles metro area. The main cable-supported span stretches 2,000 feet, including a 1,000-foot central span, flanked by two 500-foot back spans. These spans are anchored by two soaring towers, each reaching 515 feet above the ground. To manage the elevation required for such clearance, engineers designed long west and east approaches, each over 2,800 and 3,600 feet respectively. This was accomplished while maintaining manageable roadway grades of no more than 5%. The project adopted a design-build construction model, combining speed and flexibility for this complex infrastructure. Work officially began in January 2013 with a memorable groundbreaking ceremony where helicopters hovered 515 feet above ground to symbolize the height of the future towers. The bridge was built using high-performance concrete, wind-resistant cables, and deep-seated foundations, engineered to withstand both seismic activity and the enormous load demands of modern trucking and shipping logistics. The structure carries 6 lanes of Interstate 710, along with the Mark Bixby Memorial Bicycle Pedestrian Path, offering not only connectivity for commerce, but also recreational and green mobility access. Originally estimated at $800 million, the final cost of the project rose to $1.5 billion, funded through a mix of state, federal, and port agency contributions. The bridge officially opened to traffic in October 2020 and has since become a defining landmark in Long Beach. Beyond its architectural presence, the bridge enhances traffic flow, improves safety, and future-proofs a vital international trade route. It now handles billions of dollars in cargo annually, reinforcing the status of Port of Long Beach as a global shipping titan. Let's travel over. Let's talk about the Delta Conveyance project, a highly controversial yet critical $16 billion water infrastructure initiative designed to secure local water supply for the years to come. This project is largely a battle over water distribution, environmental impact, and the ability of California to handle climate change and droughts. California has always struggled with water shortages, and the Sacramento-San Joaquin Delta has been at the heart of the issue for decades. The Delta is the largest estuary on the West Coast, supplying drinking water to 27 million people and supporting 3 million acres of farmland. But climate change, aging infrastructure, and increased demand have left this water system fragile and vulnerable. The biggest threats include rising sea levels, which could push saltwater into the Delta, contaminating freshwater supplies. Levee failures put water delivery systems at risk of collapse, while the increased droughts make it harder to meet the demands of cities and farmers. To combat these challenges, the Delta Conveyance project will construct underground tunnels that transport water from the Sacramento River directly to the State Water Project system, bypassing fragile areas of the Delta. The Delta Conveyance project is designed to be a state-of-the-art water transfer system, utilizing the latest engineering and construction technologies. A 45-mile underground tunnel with a capacity of 6,000 cubic feet per second is designed to move water from the Sacramento River to the southern water systems in California. This seismic-resistant tunnel will be built using advanced tunnel boring machines capable of digging through dense soil and clay while minimizing environmental disruption. In addition to the tunnel, the project will feature new pumping stations, water treatment facilities, and intake structures that will reduce the impact on sensitive ecosystems. Unlike the current system, which relies on surface-level canals prone to contamination, the underground tunnel will protect water supply from pollutants and climate-related disruptions. The design of the tunnel incorporates earthquake-resistant engineering, ensuring that water delivery remains uninterrupted even in the event of a major seismic event. The massive scale of this project requires advanced construction techniques. The tunnel will be built using large-diameter tunnel boring machines, similar to those used in major underground projects like the Chesapeake Bay Bridge Tunnel and SR 99 Tunnel in Seattle. These giant machines will excavate at a depth of 100 feet, allowing the tunnel to pass beneath critical ecosystems and infrastructure. The Delta Conveyance project is in its final approval and permitting stage, with the construction expected to begin later in the year. The project is scheduled for completion by 2035, ultimately going to be a lifeline for millions of Californians. Next up is the billions have been poured into construction across California. And in 2025, the state's most ambitious megaprojects are finally reaching the finish line. From massive transit expansions and next-gen infrastructure to city-altering developments, these builds are about to reshape how millions live and connect. Today we reveal California's megaprojects completing in 2025 and why they'll change the future of the state forever. The California High-Speed Rail Central Valley segment is a massive feat of modern engineering, currently under construction in the heart of California's San Joaquin Valley. Spanning approximately 171 miles from Merced to Bakersfield, this corridor is the foundational spine of the state's future high-speed rail network. Designed for trains capable of reaching speeds up to 220 miles per hour, the project is setting new standards for American rail infrastructure, combining cutting-edge design with large-scale civil construction. The engineering process starts with extensive ground preparation. Central Valley soil presents a mix of challenges: expansive clay, variable water tables, and seismic activity. To address this, engineers have used soil stabilization techniques, including deep soil mixing and preloading with large berms to consolidate ground before construction. Elevated sections are supported by deep pile foundations, drilled and poured up to 100 feet into the earth to ensure long-term stability and earthquake resilience. A significant feature of this segment is the construction of numerous viaducts, overpasses, and underpasses to eliminate grade crossings and allow uninterrupted train movement. One of the most notable structures is the Cedar Viaduct in Fresno, stretching over highways and local roads, built using precast concrete segments lifted into place with specialized gantry cranes. The use of precast elements allows for faster installation and minimizes disruption to surrounding communities. In areas where the rail line cuts through farmland and residential zones, construction crews are building trench sections and using sound dampening barriers to reduce noise and visual impact. Advanced drainage systems are also being integrated to manage stormwater and protect the track from erosion and flooding. Bridges over major rivers like the San Joaquin and Kings are being constructed with seismic isolation bearings, allowing them to shift slightly during earthquakes without compromising structural integrity. These bridges involve massive steel reinforcement cages encased in high-performance concrete, designed to withstand the dynamic loads of both high-speed rail traffic and natural forces. Utilities have been a major hurdle as well. Relocating water, power, and gas lines, some decades old, requires coordination with multiple agencies and careful sequencing to avoid service interruptions. Work is progressing rapidly across all major sections, and despite delays in earlier phases, the Central Valley segment is on track for completion in 2025. Once operational, it will serve as the proof of concept for the broader California high-speed rail system, connecting the state like never before. Rising from the heart of downtown Phoenix, the Central Station East and West Towers represent a complex integration of vertical development and urban transit infrastructure. Constructed atop and adjacent to the existing Phoenix Transit Hub, these mixed-use high-rises demanded an extraordinary level of coordination between structural engineering, architectural planning, and transportation logistics. The project's objective was to transform the site into a dense, transit-oriented development that includes residential, commercial, and public amenities while maintaining uninterrupted operation of the Central Station bus and light rail services throughout construction. The first phase involved site mobilization and deep foundation work. Because the towers were to be built atop an active bus terminal, extensive structural analysis was undertaken to determine load distribution and minimize any impacts to the operational platform below. Engineers opted for a matte foundation design for both towers, reinforced with a dense grid of drilled shafts extending over 100 feet deep into competent strata. These shafts, filled with high-strength concrete and steel rebar cages, provided the vertical support necessary for the tower's substantial loads. A temporary shoring and decking system was installed above the transit level, creating a working platform that allowed construction to proceed while preserving bus operations below. This system included structural steel beams supported by temporary columns, enabling the casting of ground-level slabs without impeding passenger movement or vehicle flow. Noise and vibration controls, including insulated barriers and work-hour restrictions, were implemented to maintain the comfort and safety of transit users during critical operations like pile driving and concrete placement. Once the foundation systems were completed, vertical construction commenced using a central concrete core methodology. The core, housing elevators, stairwells, and utility risers, was formed using a self-climbing formwork system that allowed rapid upward progress while maintaining strict vertical tolerances. Simultaneously, post-tensioned concrete floor plates were constructed in successive lifts, with crews pouring and tensioning each level on a 5 to 7 day cycle. Structural columns around the perimeter were also cast in situ, reinforced with high-density steel cages to accommodate wind and seismic loads typical of high-rise structures. Mechanical, electrical, and plumbing systems were integrated into each floor plate through a coordinated building information modeling process, which allowed conflicts to be resolved before installation. Dedicated mechanical floors were spaced periodically throughout the tower to house air handling units, water booster pumps, and electrical switchgear, with vertical shafts providing routing for all distribution systems. The tower's facades combined high-performance glazing and curtain wall systems with architectural shading devices. Installation was carried out using tower cranes and swing stage scaffolding, with prefabricated curtain wall panels hoisted and anchored to embedded plates in the concrete structure. These facade systems were designed to meet energy efficiency codes and acoustic performance standards, given the site's proximity to active rail lines and bus traffic. On completion, the central station, east and west towers offered a blend of residential units, retail space, and public areas, all directly integrated with the city's transit network. The successful execution of the project demonstrated how complex high-rise construction can coexist with critical public infrastructure through meticulous planning, staged implementation, and precision engineering. The Agua Caliente solar project, located in the desert expanse of Yuma County, Arizona, is a utility-scale solar power plant that stands as a landmark in photovoltaic engineering. With a peak capacity of 290 megawatts, this sprawling installation covers over 2,400 acres and represents a highly complex blend of civil, electrical, and environmental engineering tailored to harness the sun's energy at scale in one of the most solar-rich regions in the United States. Construction of the Agua Caliente solar project began with large-scale site preparation and grading. The desert terrain, while ideal for solar exposure, required extensive earthwork to level the land and improve drainage without disrupting natural arroyos. Given the site's proximity to protected desert ecosystems, erosion control measures, such as sediment basins and silt fences, were installed early to minimize impact on surrounding lands. The project uses thin film photovoltaic technology, specifically cadmium telluride modules. Unlike crystalline silicon panels, thin film modules are more tolerant to high temperatures and low light conditions, making them ideal for the harsh desert climate. These modules were mounted on fixed tilt steel support structures anchored directly into the ground with driven steel piles. The piles were installed using GPS-guided hydraulic ramming machines that precisely positioned each foundation without the need for concrete, reducing both cost and environmental impact. Electrical engineering at this scale is a massive undertaking. The plant is divided into multiple blocks, each functioning as a semi-independent generating unit. Direct current power generated by the solar panels is routed through combiner boxes and then fed into centralized inverters that convert it into alternating current. Agua Caliente was among the first to integrate advanced inverter technology capable of dynamic voltage control and reactive power support, giving it grid stability functions typically reserved for fossil fuel power plants. To transmit the generated electricity to the regional grid, step-up transformers boost the voltage to transmission level, after which power is sent to a nearby switchyard. This switchyard was custom-built to handle the project's load and interfaces directly with the Western Area Power Administration's network, enabling the electricity to reach consumers across Arizona and beyond. Thermal management is another critical aspect. Despite the lack of moving parts in the PV modules, the inverters and transformers generate significant heat. Passive and active cooling systems, including air-cooled heat exchangers and ventilated enclosures, were deployed to ensure operational efficiency in ambient temperatures that often exceed 110 degrees Fahrenheit. Construction logistics were also a challenge due to the remote location. Over 5 million PV modules were delivered, staged, and installed using a highly sequenced supply chain. Modular construction techniques were used to pre-assemble wiring harnesses and combiner boxes, drastically reducing field labor time. Throughout the build, dust control and wildlife monitoring programs were actively maintained to comply with environmental regulations. But have you heard of Leyja? It is a magnificent step in integrating sustainable development and tourism into ecotourism. This place is situated in one of the most gorgeous natural valleys in the region and is a part of Saudi Vision 2030, which focuses on diversifying the kingdom's economy and positioning it as a leader in regenerative tourism. A destination that, at the same time, is an exhibit of modern luxury living in harmony with nature. The Valley of Leyja is a natural wonder carved by water and wind over the centuries. With cliffs rising to 400 meters, this location has been chosen for its exceptional beauty and its ability to attract eco-friendly tourists. NEOM has visualized Leyja as a destination that allows visitors to enjoy the peace of nature and all the amenities of modern times, designed to cause the least environmental impact. The 3 boutique hotels are the key to Leyja's appeal: 120 rooms and suites, all luxury. World-renowned architects have designed each of the 3 boutique hotels to blend into the rugged terrain. One of the hotels is for adventure seekers and is designed as a staircase going up the cliffs, with access to rock climbing and hiking right from the rooms. The second hotel is placed at the heart of the largest oasis within the valley and harmonizes nature with modernity as a portal to discovery. The third property is a retreat for wellness, where the guest will be soothed by relaxation and longevity, reflected in the mirror-like facade that mirrors the landscape around it. All 3 properties offer state-of-the-art wellness facilities, fine dining, and infinity pools for a combination of adventure and comfort. Leyja will be developed around the concept of sustainability. 95% of the land is being maintained as a nature reserve, hence not disturbing the ecological balance in the region. Innovative construction methods are being utilized to minimize interference with the environment. The materials and designs are selected with care to match the natural ambience, minimizing visual and ecological impact. This aligns with NEOM's overall commitment to sustainability, including renewable energy, water conservation, and eco-friendly infrastructure. From adventure to quieter activities, Leyja offers everything. It has extensive trails for hiking and guided wadi walks, which can be taken with rock climbing against the dramatic cliffs of the valley. For those who want to take it easy, the retreat offers a fine dining experience by world-class chefs and wellness programs for a more relaxed experience at the location. These attractions make Leyja a destination for all kinds of travelers. Leyja is a plan for Saudi Vision 2030 directed toward tourism development in the country. Vision 2030 is the economic transformation blueprint for Saudi Arabia, focusing on reducing its dependence on oil revenues and establishing the kingdom as a global hub for trade, investment, and tourism. Let's talk about Tilikum Crossing, the first major bridge in the United States, built exclusively for public transit, cyclists, and pedestrians. It's a bold statement of sustainability, inclusion, and forward-thinking infrastructure that has already transformed life in Portland, Oregon. Tilikum Crossing, meaning Bridge of the People in Chinook jargon, was built to connect the south waterfront of Portland with its central east side. For decades, traffic in these growing neighborhoods had been funneled through outdated infrastructure, unsuitable for growing populations and changing urban needs. Recognizing this, planners envisioned a structure not ruled by cars, but instead shaped by the people who live and move through the city every day. Construction on this visionary project began in 2011. The design selected was a cable-stayed structure with a unique feature: pentagonal towers standing 180 feet tall, supporting over 3.5 miles of Freycinet multi-tube steel cables. These cables run continuously through the tower tops, a first for any bridge in the US, creating a sleek and aerodynamic profile. The total length of the bridge is 1,720 feet, with a 780-foot main span and 4 piers, 2 on land, 2 in the river. The deck is divided into 3 lanes. The center holds 2 rail tracks used by Max Orange Line light rail trains, TriMet buses, and the Portland Street Car. The project cost approximately $135 million, funded through a combination of federal grants, state lottery funds, and local sources. Builders utilized custom river barges, piling rigs, and specialized concrete casting systems to execute construction with minimal impact on the river and surrounding ecosystems. But what truly sets Tilikum Crossing apart is its interactive LED lighting system. Created by artists Anna Valentina Murch and Doug Hollis, the system dynamically responds to real-time data from the Willamette River, its temperature, speed, and depth, translating these measurements into a living light show that animates the bridge each night. Completed and opened to the public on September 12, 2015, Tilikum Crossing has since become a symbol of the commitment of Portland to green transportation and community-driven infrastructure. In recent years, TriMet has continued to innovate, adding 12 vertical axis wind turbines to the bridge in 2019, each generating power and adding to the structure's sustainability profile. Next up, let's travel over to the most ambitious transit expansion in California, the Transbay Transit Center Phase 2 in San Francisco. Initially envisioned as the Grand Central of the West, this multi-billion-dollar expansion is meant to integrate high-speed rail, commuter rail, and local transit into a seamless transportation hub. The Transbay Transit Center project was first proposed in the early 2000s, with the goal of revamping the aging Transbay terminal and expanding rail connectivity. The first phase, completed in 2018, included a modern, multi-level transit center designed to accommodate local buses and future rail connections. However, Phase 2, which focuses on bringing Caltrain and the future California high-speed rail into downtown San Francisco, has been significantly delayed due to multiple reasons. The project is critical for the long-term transit future of the Bay Area. Currently, the northern terminus of the line is in San Francisco at 4th and King Street, 1.3 miles away from downtown San Francisco. This disconnect forces passengers to transfer to buses or other transit services, creating inefficiencies and increasing congestion. Phase 2 will finally allow seamless connections between high-speed rail, regional rail, and local transit, improving commuting times and reducing carbon emissions at large. Once completed, a train ride from San Francisco to Los Angeles will take just over 3 hours. The project involves 3 underground train platforms designed to handle both high-speed and commuter rail services. These platforms will be built beneath the existing Transbay Transit Center, allowing direct access for passengers to financial district destinations. The tunnel will also feature state-of-the-art seismic resilience, crucial for an area prone to earthquakes and ground shifts. Engineers are implementing deep foundation techniques and advanced tunneling methods to ensure the infrastructure can withstand significant seismic activity. The total cost of Phase 2 has skyrocketed to over $6 billion, making it one of the most expensive transit expansions in the country. A significant portion of this budget goes toward property acquisition, tunneling challenges, and modern engineering solutions. The complexity of underground construction in a densely populated city has also driven up costs, requiring specialized labor, advanced tunneling techniques, and extensive permitting processes. The construction is progressing steadily, with an estimated completion date of 2032. Next up, we have to talk about the West Harbor development is a major waterfront revitalization project transforming a 42-acre site along the Port of Los Angeles in San Pedro. Once home to the aging Portugal village, this area is being reimagined into a vibrant commercial, dining, and entertainment district that reconnects the public with the harbor. With its grand opening slated for 2025, the West Harbour development is not just about creating a new destination. It's a complex engineering and construction effort that redefines how urban spaces interact with working ports. The site sits along an active stretch of waterfront, which brings both opportunity and challenge. The first phase of construction involves significant demolition and environmental remediation. Old utility lines, some dating back over 70 years, had to be removed or upgraded. Soil stabilization was also crucial, as parts of the site had been filled in decades earlier, requiring deep soil compaction and the installation of stone columns to reinforce the foundation before any vertical construction could begin. Structurally, the buildings at West Harbour are being engineered to withstand both seismic loads and corrosive marine conditions. Foundations are a mix of driven piles and shallow footings, depending on soil depth and proximity to the water. Exposed structural steel is being treated with marine-grade coatings, and concrete mixes are specially designed with high sulfate resistance to endure the salty coastal environment. A signature element of the project is the open-air amphitheatre, positioned right on the water's edge. Its tiered seating and canopy system are being constructed using pre-stressed concrete and steel trusses anchored deep into the harbour embankment. Adjacent to that, a new public promenade stretches nearly a mile along the waterfront, built with a combination of cast-in-place and precast concrete panels, with integrated lighting, utilities, and stormwater management systems hidden beneath. To support the high volume of visitors expected, new access roads and parking structures are also being built, along with utility corridors that include water, power, fiber optics, and advanced fire protection systems. Much of this infrastructure is being installed underground, requiring careful coordination with existing port operations and local agencies. West Harbour's construction blends civic design, heavy infrastructure, and environmental considerations into one cohesive plan. With restaurants, retail, event spaces, and waterfront views, the development is poised to become a landmark destination. As it nears completion in 2025, it's not just transforming the San Pedro waterfront. It's reshaping how communities engage with industrial harbours across the country. Some transportation corridors evolve from long-range planning models into fully realised infrastructure only after extensive engineering, environmental, and political groundwork. Arizona State Route 505 followed such a trajectory, conceptualized to serve as a critical connector within the state's expanding highway network. Designed to link developing suburban zones with major interstate corridors, the highway's construction presented a variety of technical and logistical complexities due to its alignment through mixed-use areas, including undeveloped land, residential communities, and light industrial zones. Site development for State Route 505 began with comprehensive right-of-way acquisition and environmental compliance measures. Land surveys were followed by extensive geotechnical borings to assess soil composition, moisture content, and bearing capacities. These tests identified areas where the subgrade required stabilization, particularly in floodplain-adjacent sections where clay-rich soils had the potential for seasonal swelling. To address this, engineers specified lime stabilization and geotextile reinforcements beneath the roadbed to distribute loads and maintain long-term performance. Clearing and grubbing operations removed vegetation and surface obstructions, while sediment control measures such as silt fencing and stormwater inlet protections were installed to meet environmental permitting requirements. The highway's profile grade was established using precision GPS-enabled dozers and graders, ensuring proper slope for drainage and vehicular safety. Embankment fills were compacted in lifts using vibratory rollers, and settlement monitoring devices were embedded in critical zones to track ground movement over time. Pavement structure for State Route 505 was built to accommodate projected heavy truck traffic. The typical cross-section consisted of a thick aggregate base course over which hot mix asphalt was placed in multiple lifts. In higher stress areas, such as intersections and climbing lanes, polymer-modified asphalt was specified to increase rut resistance and fatigue life. Longitudinal and transverse joints were sealed with bituminous compounds to prevent water infiltration. Interchanges along the corridor featured modern diamond and single-point urban interchange designs, depending on traffic volumes and right-of-way constraints. These interchanges required deep excavation for underpasses and extensive use of mechanically stabilized earth walls, which were constructed using alternating layers of compacted fill and steel or polymer reinforcement grids. Bridge structures utilized precast, pre-stressed concrete girders supported on drilled shaft foundations with abutments integrated into the retaining wall systems for space efficiency. Intelligent transportation systems were embedded throughout the corridor, including ramp metering systems, overhead dynamic message signs, traffic detection sensors, and fiber optic communication lines linked to regional traffic management centers. Roadside infrastructure included LED lighting mounted on galvanized steel poles, breakaway sign supports, and crash attenuators placed at key impact points to enhance roadside safety. Drainage infrastructure was extensive, consisting of reinforced concrete pipe networks, box culverts, and bioswales designed to control stormwater runoff. These systems were modeled to accommodate 100-year storm events, with detention basins strategically located to manage peak flows without overburdening downstream channels. Upon completion, State Route 505 provided not only an essential transportation corridor for central Arizona, but also demonstrated the integration of advanced highway engineering practices with long-term urban planning goals. Its execution underscored the importance of scalable design, phased construction, and resilient materials in modern roadway development. Arizona is in the middle of a transformation so massive, it's turning the desert into the most aggressively developed regions in the country. From billion-dollar tech hubs rising out of nowhere to infrastructure unlike anything the state has ever seen, these mega projects are rewriting Arizona's future in real time. Today, we uncover the biggest mega projects in Arizona and how they're redefining what this state is capable of. In the heart of modern semiconductor production lies one of the most advanced facilities ever constructed, a TSMC semiconductor fabrication plant, often referred to as a fab. These massive facilities are far more than just factories. They are precisely engineered ecosystems where physics, chemistry, and nanotechnology converge in extreme harmony. At its core, the construction of a TSMC Fab begins with site selection that prioritizes geotechnical stability. Even minor vibrations from seismic activity or traffic can jeopardize the ultra-precise lithography processes. Once the site is chosen, deep foundation work begins, often involving pile driving and seismic base isolation systems to counteract natural tremors. Massive steel-reinforced concrete slabs are poured with tolerances tighter than most bridges or high-rises to ensure absolute levelness across the fab floor. Inside the fab, the environment must be tightly controlled. Air purity, temperature, humidity, and vibration levels are kept within razor-thin margins. The clean room is the centerpiece, classified as ISO class 1 or 2, meaning it contains less than 10 particles per cubic meter, smaller than a micron. This is achieved through a labyrinthine network of HEPA and ULPA filtration systems, airlocks, and positive pressure airflow. Air circulates top-down, pulled through raised perforated floors, and recirculated after filtering contaminants, maintaining laminar airflow that prevents turbulence around wafer surfaces. Above the cleanroom lies one of the most complex engineering feats, the subfab and utility floors. These multi-level platforms house the chemical delivery systems, vacuum pumps, gas cabinets, and waste handling systems. All utilities are routed here to isolate vibration and electromagnetic interference from sensitive photolithography and etching equipment. Chemicals like arsine, phosphine, and fluorine gases are piped through triple-contained conduits equipped with sensors to detect the slightest leak, triggering immediate shutdown protocols. Structural engineering plays a critical role in equipment placement. Tools like EUV lithography machines, some weighing over 180 tons, require foundations independent from the rest of the building, often mounted on vibration-dampening platforms and inertial masses to eliminate microshifts. To maintain process integrity, utility redundancy is key. Power supplies feature multi-tiered backups with diesel generators, flywheel UPS systems, and dual feeds from the grid. Water purification systems generate ultra-pure water at millions of gallons per day, removing even sub-nanometer contaminants, critical for rinsing wafers. Let's travel over to Vladivostok, Russia, where the Russky Island Bridge is located, covering an enormous 1,872 meters, with the world's longest cable-stayed span. This bridge connects the mainland to the formidable Russky Island. The Russky Island Bridge wasn't just for show, it had a purpose. It was the centerpiece of infrastructure upgrades for Vladivostok as the city prepared to host the Asia-Pacific Economic Cooperation Summit in 2012. Before the bridge, Russky Island, which housed the summit's conference center and new federal university, was largely inaccessible. The bridge made it a lively hub, directly connected to the mainland and demonstrating Russia's engineering skills to world leaders. What makes the Russky Island Bridge so amazing? For one, it is built to withstand Siberian winters and harsh marine conditions. Temperatures in the region can drop to as low as -40 degrees Celsius, and the bridge is designed to meet design wind speeds of 36 meters per second. To further extend these conditions, engineers went beyond that. On top of the deck, towering structures of the tallest bridge towers in the world are found, 320 meters tall. These are balanced with piles driven as deep as 77 meters into the ground, balancing any windy or icy conditions. But it's not just the pylons. The cable system of this bridge is a marvel of engineering. Ultra-compact cables on the Russky Island Bridge, which can bear heavy loads and reduce resistance due to wind, are part of the main structures. Such cables range up to 580 meters and are made of strands of high-strength steel wires that have a protective sheath. This design reduces the amount of cables but also decreases wind load on the structure by up to 30%. This feature alone saved the pylons and deck tremendous material and construction costs. It was not easy to build such a huge bridge. Russian contractors collaborated with international experts for this. The French engineering company Freeway was essential in the design and installation of the cable system and provided technical support throughout the project. It was also a record-breaking bridge with the largest size and weight of its cables, weighing 65 tons each for the longest ones. Installing those cables, especially in freezing conditions, was an enormous task, pushing the limits of engineering and logistics. The Arthur Ravenel Jr. Bridge, the tallest and longest cable-stayed bridge in the southeastern United States, spanning over the Cooper River in Charleston, South Carolina. This architectural marvel spans a total length of 13,200 feet, with a main span of 1,546 feet, ranking it among the longest cable-stayed spans in North America. The bridge carries 8 lanes of traffic and includes a dedicated pedestrian and bike path. This makes it a vital transportation artery and a famous community landmark. The bridge was built in response to a dire need. The previous crossings, the Grace Memorial Bridge from 1929 and the Pearman Bridge from 1966, had become structurally and functionally obsolete by the 1980s. These aging truss bridges couldn't accommodate modern vehicle loads or the larger cargo ships headed to the ports in Charleston. One even scored an alarming 4 out of 100 in safety assessments. That urgency sparked a political and public movement, championed by Arthur Ravenel Jr., a former US congressman who later became a state senator. In recognition of his role, the bridge was named in his honor, though not without some public debate. The bridge features 2 diamond-shaped towers, each standing 575 feet tall, supporting 128 cables that suspend the road deck 186 feet above the river. This complex yet intelligent design accommodates the largest container ships in the world to pass beneath, a critical need for the growing port economy of Charleston. To resist the volatile weather and seismic history of Charleston, the bridge was engineered to withstand earthquakes of magnitude 7.4 and hurricane-force winds exceeding 300 miles per hour. Rock islands protect the towers from ship collisions, and all components are built to endure decades of heavy use. The construction was executed by Palmetto Bridge Constructors, a joint venture between Tidewater Skanska and Flatiron Constructors. The final cost of this mega project reached $700 million. Using design-build methods, workers started building even before the final plans were completed. Tower segments were assembled using a self-climbing formwork system, allowing quick and efficient work hundreds of feet in the air. Crews worked around the clock, installing sections of the deck outward from both towers while suspending new cables in tandem. The bridge officially opened on July 16, 2005. After 4 years of fast-paced construction, it replaced both the older bridges, which were demolished soon after. Since then, the Ravenel Bridge has become a beloved fixture of Charleston, frequently appearing in pop culture, postcards, and even video games. The bridge carries over 96,000 vehicles daily, nearly reaching its forecasted 2030 capacity more than a decade early. But just wait until you hear about the Olympic and Hill Tower, a massive 60-story skyscraper that is set to reshape downtown Los Angeles. This ambitious project represents a bold leap in the vertical expansion of the city, introducing luxury residences, office spaces, and high-end retail into a single state-of-the-art urban development. Los Angeles has long been a city known for its low-rise spread, but recent years have seen a shift toward high-density vertical developments. The Olympic and Hill Tower features 685 rental apartments, ground floor retail, a comprehensive amenity package, and parking for over 1,000 vehicles. Positioned at the intersection of Olympic Boulevard and Hill Street, this mega project is designed to cater to the growing demand for high-rise living, reflecting the shift of the city towards a transit-friendly future. Standing at an impressive 800 feet, the Olympic and Hill Tower will be among the tallest buildings in Los Angeles once completed. The sleek, modern design of the tower is not just for aesthetics. It integrates cutting-edge sustainability features, making it one of the most energy-efficient skyscrapers in the city. The eco-friendly glass facade will significantly reduce heat absorption, keeping interiors cooler while lowering energy consumption. Additionally, the automated smart home technology of the building will introduce AI-controlled climate and lighting systems. This allows residents to adjust temperature, lighting, and security features through a centralized digital interface. The construction of the Olympic and Hill Tower is no small feat. The project involves the use of high-strength steel framing, advanced seismic reinforcements, and prefabricated modular components to ensure structural integrity while expediting construction timelines. Given the seismic risk in California, engineers are integrating earthquake-resistant technologies, including shock-absorbing materials and a reinforced concrete core to enhance building stability. The estimated cost of the project exceeds $700 million, covering land acquisition, engineering, material procurement, and labor. Developers are utilizing crane-assisted construction, automated robotic scaffolding, and precision-guided lifting equipment to assemble prefabricated sections of the tower. This method not only reduces waste, but also enhances construction speed, ensuring that the building meets its expected completion deadline. Currently, the construction is in full swing, with several floors already taking shape. Shortly after construction began, it was revealed the original building height was shortened from 760 feet to 590 feet, along with the building getting shortened from 60 stories to 54 stories. Currently, the foundation and core structure are being reinforced, while the upper floors are progressively rising. The project is on track for a 2025 completion, at which point it will redefine luxury living in Los Angeles. Let's move over. The San Francisco Central Subway project is one of the most technically demanding and transformative transit undertakings in the Bay Area. Designed to extend the Muni Metro T third line through some of the city's busiest and most congested neighborhoods, the project adds 1.7 miles of track, mostly underground, linking the southern end of the city with downtown, Chinatown, and Union Square. After years of complex construction and tunneling beneath the city's dense urban fabric, the project reached major completion milestones and opened for service, but full integration and refinement of systems will continue into 2025. Engineering an underground subway in a city like San Francisco is no simple task. The Central Subway consists of twin tunnels, each roughly 21 feet in diameter, constructed using two earth pressure balanced tunnel boring machines nicknamed Mom Chung and Big Alma. These TBMs started their journey from the south of Market area, working northward beneath key infrastructure, including major sewer lines, building foundations, and active utility corridors. Maintaining ground stability was critical, especially given San Francisco's mix of soft soils, fill material, and seismic vulnerability. As the machines moved forward, they installed precast concrete tunnel lining segments, which were bolted together to form a continuous structural ring, immediately supporting the tunnel walls. The alignment includes 3 new underground stations: Yerba Buena, Moscona, Union Square, Market Street, and Chinatown, each constructed using cut and cover or sequential excavation techniques depending on site conditions. At Union Square, excavation had to proceed beneath an active shopping district, requiring engineers to install deep slurry walls and steel bracing systems to hold back the earth while construction crews worked below. Massive jet grouting operations were used to stabilize the soil before excavation, and utility lines were rerouted around the construction site, often requiring delicate, hand-dug access pits to avoid service disruptions. The Chinatown station, sitting 100 feet underground, is one of the deepest in the Muni system. Excavation here took place within a reinforced concrete box structure, with deep pile foundations anchoring it into bedrock. Ventilation shafts, emergency egress routes, and mechanical systems had to be integrated vertically due to the limited footprint at street level. In the heart of the Sonoran Desert, the expansion of Phoenix's Valley Metro Rail into the South Central Corridor stands as a testament to integrated urban infrastructure and the challenges of building transit lines within an active metropolitan grid. The South Central Extension represents a critical upgrade to the region's transportation network, stretching over 5 miles in length and connecting downtown Phoenix to the underserved communities along South Central Avenue. From the earliest planning phases, engineers and construction teams faced numerous logistical and technical hurdles that required careful orchestration and innovation. The initial phase involved comprehensive subsurface utility engineering. Before any excavation could begin, teams deployed ground-penetrating radar and vacuum excavation to identify and map buried utilities such as gas mains, water lines, electrical conduits, and fiber optic cables. These utilities needed to be either protected in place or relocated entirely. Once mapping was complete, utility relocation began in phases to avoid service disruptions to residents and businesses. Concurrently, crews worked to establish temporary traffic control measures to maintain access along South Central Avenue, a heavily traveled arterial road. Site grading and roadbed preparation came next. Earthwork involved removing existing pavement and regrading to establish subgrade elevations that aligned with the future track alignment. Stormwater management posed a unique challenge due to the region's susceptibility to flash flooding. Civil engineers incorporated a network of underground drainage structures and retention basins designed to intercept and detain stormwater runoff, particularly around intersections and low-lying zones. Track installation commenced with the precise layout of the guideway. Using laser surveying and GPS-based control points, the track center line was marked, and crews began excavation for the ballastless track slab foundation. A reinforced concrete slab was poured in segments, followed by placement of embedded direct fixation fasteners to hold the rail in position. Continuous welded rail was delivered in long lengths and thermite welded on site to ensure a seamless, low-maintenance riding surface. Alignment tolerances were kept within strict specifications using precision jigs and hydraulic rail positioners. Simultaneously, construction of the traction power substations and overhead catenary system advanced. The substations, spaced strategically along the corridor, required deep foundations and high-voltage switchgear installations. Overhead contact system poles were erected using truck-mounted augers and cranes, and tensioned copper contact wire was strung in sections, later adjusted for sag and alignment. The system included automatic tensioning devices to account for thermal expansion in the desert heat. Station construction featured reinforced concrete platforms built to accessibility standards, with integrated canopy structures providing shade and shelter. Each station was equipped with passenger information systems, fare vending machines, lighting, and public art elements designed in coordination with local artists. Landscaping utilized drought-tolerant plantings and drip irrigation to align with regional sustainability goals. The project also included new signalized intersections and traffic signal priority systems, enabling trains to move through cross streets efficiently. Roadway reconstruction, including new pavement, sidewalks, and bike lanes, was integrated into the final phases to ensure multimodal connectivity. Throughout the build, community outreach and phased construction scheduling played a vital role in minimizing disruptions and maintaining stakeholder support. The South Central extension ultimately reinforced the importance of equitable transit access and showcased the complexities involved in urban light rail construction within an established city framework. Rising from the Arizona desert near the banks of the Salt River, the VAI Resort is a construction project unlike anything else in the Southwest, a massive entertainment and hospitality complex engineered to bring the grandeur of Las Vegas and Miami nightlife to the heart of the Phoenix metro area. With over 1,000 luxury rooms, a 360-degree concert stage, and an artificial lagoon at its center, VAI isn't just being built to impress. It's being built with a level of engineering precision that transforms a leisure destination into a structural marvel. The construction of VAI Resort begins with large-scale earthworks and soil stabilization. The area's naturally sandy and loose soil profile required pre-compaction and ground improvement techniques, including the use of vibro-compaction and deep soil mixing to prepare the terrain for the resort's heavy superstructure. A major challenge came with the creation of the man-made lagoon, which spans over 6 acres. Engineers had to design an impermeable liner system beneath the lagoon to prevent water seepage into the desert soil, while also integrating circulation and filtration systems that can maintain clean, swimmable water in a hot climate where evaporation is a constant threat. Structurally, the resort consists of multiple high-rise hotel towers, each supported by deep concrete piles drilled and anchored into dense soil layers below. Because of the harsh summer temperatures, often exceeding 110 degrees Fahrenheit, The building envelope was designed with advanced thermal performance in mind. High-performance glazing systems, reflective roofing membranes, and ventilated facades reduce solar heat gain while maintaining visual appeal. This isn't just for energy efficiency, it's critical for guest comfort and building longevity. One of the standout engineering features is the amphitheater-style concert venue built into the core of the resort. Designed to accommodate thousands of guests, it required the integration of acoustic isolation materials and vibration control systems to avoid sound bleed into the adjacent hotel towers. Massive trusses span the concert arena to support lighting, audio systems, and pyrotechnic rigs, all while withstanding Arizona's monsoon winds. Behind the scenes, the mechanical systems are laid out with the precision of a data center. Chilled water plants feed into an extensive network of air handlers, and modular HVAC zones allow independent climate control across various entertainment zones, hotel wings, and dining areas. Energy recovery systems and solar integration play a role too, with photovoltaic panels installed across rooftop terraces and shade structures. From pile cap to penthouse, VAI Resort is engineered as both an entertainment powerhouse and a self-contained micro-city, one that showcases not only bold design, but also the raw technical mastery required to bring it to life in one of the country's most extreme climates. Next up, we can't forget to talk about the Sejong City Megaproject. Designed as a hub for administrative efficiency and technological innovation, the city project was established to decentralize government functions and ease the pressure on the overpopulated capital, Seoul. It represents South Korea's vision for a sustainable and balanced future. Sejong is meticulously planned in terms of layout and infrastructure. The smart city technology utilized allows for efficiency in urban management. IoT-enabled systems monitor everything from energy consumption to the traffic flow. That way, resource optimization takes place. The examples include sensor-assisted collection of waste and, thus, intelligent timing of adjustment by traffic lights. These innovations place Sejong at the pinnacle of developing a smart city. Design considerations of this city consider livability along with technological advancement. The city had residential areas, schools, restaurants, and community spaces that were highly developed. Over the years, it became easy for public officials and their families to stay in the city. To date, most of the unavailability of amenities that caused most families to commute from Seoul is corrected. Now, Sejong presents a very well-balanced urban way of life, with both modern conveniences and access to green space. It is also worth noting that Sejong functions as a pilot city for smart cities. The management of the city integrates high-tech digital tools for the administration of public business, which leads to easier decision-making and streamlined operations. This strategy, however, received its share of criticisms as well. While it pays attention to technology, at times, it forgets and neglects human needs, such as cultural infrastructure and personal relationships in the neighborhood. Although Sejong has faced all these challenges, it is growing to be one of the great models for urban planning. Ministries have steadily been relocated in the city, and there are further plans, including better links in transportation, as well as cultural facilities. So far, Sejong houses many officials, and the population is increasing with a contribution to the economic and social vibrancy of the city. The Dale Gardner Veterans Memorial Bridge, a critical Mississippi River crossing connecting Illinois and Iowa, known as the New Savannah-Sabula Bridge. This structure replaced the aging and narrow Savannah-Sabula Bridge, a truss bridge that stood for decades but could no longer support the increasing demand and modern traffic requirements. The Dale Gardner Bridge is a steel tied arch bridge carrying US Route 52 across the Mississippi River. Construction began in 2016, and the bridge officially opened to traffic on November the 17th, 2017. Named after Dale Gardner, a US Navy captain and NASA astronaut born in nearby Fairmount, the bridge not only carries vehicles, but also honors a local American hero. The design features a 2,500-foot span engineered for strength, durability, and safety. Its dual-lane configuration helps accommodate both commercial and commuter traffic, replacing the outdated predecessor that often bottlenecked vehicles crossing between the two states. The tied arch design was chosen for its aesthetic appeal and ability to efficiently distribute weight while spanning the wide Mississippi. The project employed high-strength structural steel, reinforced concrete piers, and automated construction cranes to efficiently and precisely assemble the massive components. The erection process was closely monitored due to the complexity of lifting and placing the arch segments over the river. The design team selected the steel tied arch option for the navigation span and steel girders for the approach viaducts. These structure types and the preferred offset alignment best satisfied the evaluation criteria, including environmental impact, maintenance of traffic, structure maintenance, and aesthetics. With a budget of approximately $80 million, this project included more than just the main span. It required significant investment in approach roads, causeways, and environmental protection measures. However, shortly after the bridge opened, a major issue emerged. In 2018, the bridge was closed when the adjacent Running Slough Bridge, part of the approach causeway, began to sink between 1 to 5 feet, prompting immediate safety concerns. This closure forced travelers into a 36-mile detour through Clinton, Iowa, and Fulton, Illinois. In response, authorities launched a temporary ferry service between Savannah and Sabula beginning June 12, 2018, to reduce the impact on local communities and businesses. The bridge finally reopened on August 31, 2018, once the new causeway was completed and declared safe. Now fully operational, the Dale Gardner Veterans Memorial Bridge serves as a key corridor for freight and regional traffic, enhancing connectivity between Illinois and Iowa. Let's move over to the Calexico West Land Port of Entry modernization, a game-changing infrastructure project aimed at revolutionizing border security and trade between the United States and Mexico. Located in Calexico, California, this $400 million project is one of the largest border crossing upgrades in the country, expanding capacity, increasing efficiency, and strengthening national security. The Calexico West Land Port of Entry is one of the busiest border crossings between California and Mexico, serving millions of travelers and commercial trucks each year. The port connects Calexico, California to Mexicali, Mexico, a major hub for manufacturing, trade, and commerce. However, the aging infrastructure and increasing congestion have led to long wait times, security vulnerabilities, and inefficiencies that hamper the flow of goods and people. The modernization project, managed by the General Services Administration, is being executed in 2 phases. Phase 1, completed in 2018, involved the relocation and expansion of southbound traffic lanes, a new head house for Customs and Border Protection officers, and additional inspection booths to improve efficiency. Phase 2, currently under construction, includes expanding northbound lanes, adding new commercial vehicle processing areas, and upgrading pedestrian crossings. Security remains a top priority in the project, with the integration of cutting-edge surveillance and scanning technologies. The upgraded port will feature license plate recognition systems, enabling faster and more accurate vehicle processing. Additionally, radiation detection and cargo scanning systems will enhance the ability to identify contraband and hazardous materials before they enter the United States. Automated pedestrian processing kiosks are also being introduced to expedite foot traffic and reduce long wait times. The impact of the project on trade and travel cannot be overstated. Mexicali is a major manufacturing and commerce hub, and the Calexico port plays a crucial role in facilitating the movement of goods across the border. Once completed in 2026, the upgraded port will significantly cut wait times, allowing businesses to transport goods more efficiently. Travelers will experience smoother and more secure processing, improving overall border crossing experiences. The machinery employed in this project includes high-capacity cranes, heavy-duty earth movers, and specialized concrete pouring machines, ensuring rapid and precise construction. Advanced tunnel boring machines and automated assembly equipment are also being utilized to construct underground security corridors for customs and border protection personnel. The San Diego Airport Terminal 1 replacement project is one of the largest infrastructure upgrades in Southern California, aimed at modernizing and expanding the aging terminal to meet growing passenger demand while improving operational efficiency. Originally opened in 1967, the existing Terminal 1 has long struggled with outdated facilities and limited capacity. The replacement effort, currently under full-scale construction and scheduled for completion in 2025, is not just a renovation. It's a complete teardown and rebuild from the ground up. The new Terminal 1 will feature 30 gates, up from the original 19, and is being constructed in multiple phases to keep the airport operational throughout the project. Demolition of the old terminal began with surgical precision, using high-reach excavators and selective deconstruction methods to safely dismantle the structure without disrupting adjacent taxiways, utilities, or nearby active terminals. Crews carefully capped and relocated decades-old water, electrical, and fuel lines running beneath the old foundation before any major excavation could begin. The replacement terminal is being built on deep foundations, including large-diameter drilled piers that reach down into stable coastal soils. These foundations are tied into reinforced concrete pile caps, which support the structural steel frame of the terminal building. The steel superstructure rises in a series of connected modules, each erected with large crawler cranes hoisting beams, columns, and trusses into place. Crews are sequencing steel erection with slab pours, fireproofing, and curtain wall installation in tightly coordinated steps to maintain construction momentum. One of the standout features of the new terminal is its massive glass facade, designed to maximize daylight and provide panoramic views of the airfield and San Diego Bay. These curtain wall systems are supported by custom steel mullions and integrate bird-safe glazing, advanced UV coatings, and embedded shading devices to reduce solar gain. The terminal's roof system includes long-span steel trusses designed to accommodate wide, open concourses and mezzanines, with mechanical systems tucked neatly into the plenum space. Inside, the terminal will house upgraded baggage handling systems, new TSA checkpoints, automated check-in kiosks, and expansive concessions and waiting areas. Beneath the public levels, complex mechanical, electrical, and plumbing systems are being installed in stacked utility corridors, with seismic bracing and flood protection features designed to meet California's latest building codes. Beyond the terminal building, the project includes a major overhaul of the airport's roadway network. Crews are constructing new access ramps, elevated roadways, and a new on-airport entry plaza to separate arriving and departing traffic. Integrated into this is space for a future people mover system that will eventually connect the terminal to regional transit hubs. The South Central Light Rail Extension in Phoenix is a transformative transit project engineered to connect the city's downtown core with its historically underserved South Central Corridor. Spanning approximately 5 miles from downtown Phoenix to Baseline Road, this extension is more than just a transportation upgrade. It's a highly complex, multi-phase civil engineering endeavor aimed at enhancing mobility, urban development, and infrastructure resilience in a dense urban environment. Construction begins with deep utility coordination. Unlike new freeway builds, light rail through existing neighborhoods requires extensive underground work. crews must first relocate or upgrade water mains, gas lines, sewer systems, storm drains, and electrical conduits, many of which are decades old and poorly documented. Trenching is done in narrow corridors with limited clearance, often using vacuum excavation and hydro excavation to avoid damaging live utilities. This stage alone can span over a year, as utility realignment must occur before track work can begin. Once utilities are relocated, structural groundwork begins. The rail guideway is built on a reinforced concrete slab track system embedded directly into the roadway, which minimizes vertical elevation change and maintains a flush surface with traffic lanes and pedestrian crossings. Continuous welded rail is used to reduce noise and maintenance, and it's anchored in elastomeric pads to mitigate vibration, crucial in residential zones and near schools or businesses. In areas with heavy traffic congestion, like Central Avenue, engineers had to design a shared right-of-way where light rail vehicles run in dedicated lanes, separated by raised curbs or textured paving. Signal prioritization technology is integrated at intersections, giving light rail vehicles green lights in sync with their schedule while still allowing cross-traffic flow through coordinated signal timing. Bridge and overpass modifications are also part of the project. The extension includes upgrades to existing structures to meet modern load, seismic, and ADA requirements. Where the line crosses the Salt River, for instance, an entirely new bridge was constructed adjacent to the original freight alignment. This bridge uses pre-stressed concrete girders and deep drilled shafts to withstand flooding and seasonal ground shifting, particularly important in Arizona's expansive soils. Stations are designed as urban mini-hubs, with platforms that feature tactile paving for the visually impaired, shade structures engineered to maximize cooling via passive ventilation, and integrated lighting for safety and aesthetics. Each station also has underground conduit infrastructure for future utility upgrades, fare system improvements, or surveillance integration. Throughout the project, Valley Metro implemented an innovative phased construction approach to minimize disruption. Work zones were rotated systematically to allow local businesses continued access, and precast elements, such as station platform components and utility vaults, were manufactured off-site and installed rapidly to reduce on-site construction time. About the West Harbor development, a $500 million waterfront transformation that is set to redefine the coastline of Los Angeles. This ambitious project is replacing the iconic but aging Ports O'Call Village, which once stood as a popular waterfront attraction. The area lost its appeal due to outdated infrastructure, lack of investment, and competition from newer developments across the city. The development is being built on 42 acres on the former site of Ports O'Call Village. The food hall will house 5 restaurants, 15 food stalls, and numerous retail shops. The development will also feature a 6,200-seat amphitheater designed to host concerts, cultural performances, and large-scale events. This venue is expected to become a major attraction for both locals and tourists, drawing top-tier entertainment to the Los Angeles waterfront. Currently, West Harbor is among the most significant real estate developments on the West Coast. The project involves major demolition and reconstruction efforts requiring specialized heavy machinery such as excavators, cranes, and pile drivers to create a solid foundation for the new structures. Advanced modular construction techniques are also being used to speed up the building process, allowing for more efficient assembly while maintaining the highest standards of quality and safety. The construction on West Harbor is well underway, with key structures taking shape and final design elements being refined. The project is on schedule for its anticipated grand opening in 2026, promising to revitalize the waterfront economy of Los Angeles. We have to talk about the Louisiana Highway 1 bridge, one of the longest and most important bridges in the United States. Spanning the wetlands of Louisiana, This bridge plays a crucial role in connecting oil refineries, ports, and local communities. Located in Lafourche Parish, the bridge spans Bayou Lafourche and the surrounding marshes, connecting Leeville to Port Fourchon, a key support hub for offshore oil platforms in the Gulf of Mexico. With a total length of over 43,600 feet, it ranks among the longest bridges in the world. What makes it even more significant is its role in maintaining uninterrupted access to Port Fourchon, which services approximately 90% of the deepwater oil production in the Gulf. The bridge first opened to the public in 2009. It was designed to replace the low-lying sections of the original Louisiana Highway 1, which were frequently flooded and damaged during storms and hurricanes. Given its critical location and purpose, the new structure was engineered to be high above sea level, offering resistance to flooding, storm surges, and sea level rise. Engineers took into account the coastal erosion and subsidence challenges unique to southern Louisiana. The elevation of the bridge makes it one of the few reliable evacuation routes in the region during hurricane season. The construction plan involved elevating an 18-mile stretch of highway across some of the most fragile ecosystems in the country. The solution came in the form of a concrete trestle design, which distributes the weight of the structure evenly and minimizes impact on the marshland below. This method allowed crews to drive deep pilings into the marsh using specialized marine construction rigs and high-capacity cranes, ensuring long-term structural integrity in a highly unstable environment. The overall project cost sits around $1.5 billion, much of which was allocated for advanced materials, environmental protections, and large-scale logistics. A combination of precast concrete segments and on-site poured elements ensured strength and durability while keeping the pace of construction efficient. The machinery employed included piling barges, mobile bridge launchers, and marine cranes, allowing workers to assemble the bridge incrementally over water and unstable ground. While a major portion of the bridge is already operational, the expansion northward to Golden Meadow is still underway. The full completion of the bridge is targeted for 2030, and once finalized, it will create a fully elevated corridor stretching from Golden Meadow to Port Fourchon. Let's discuss. We have to talk about the Stargate project, an advanced AI supercomputer launching in 2028. Microsoft and OpenAI are not only putting together a supercomputer, but also creating a network of data centers spread across 5 phases. One may think of the building blocks, each phase 1 step at a time, which brings one new level after another of new power and capabilities. They stand at phase 3 today. Until 2026, they should come up with an even smaller but the same supercomputer, which is in the 4th phase. $100 billion is a term so ludicrous it comes straight from a lottery ticket. In terms of actual figures, it represents one of the costliest technological ventures ever undertaken. Why is it so pricey? For one thing, such a huge chunk goes to the core of the system. AI chips. These are no ordinary chips for computers because they are very advanced processors handling tremendous amounts of data at lightning-fast speeds. More to the point, these processors are sourced from NVIDIA, the industry leader currently. Each chip sold costs as much as $40,000. For instance, the NVIDIA Blackwell B200 is the chip that will bring Stargate to life. The chips are designed with high-performance AI tasks in mind, such as complex calculations and machine learning processes. With demand for AI chips skyrocketing, these chips become the center point of cost for this project. To the Wallace Annenberg Wildlife Crossing, a first-of-its-kind ecological bridge helping animals safely cross the 101 Freeway in Southern California. This first-of-its-kind ecological bridge is set to become the largest wildlife crossing in the world, spanning more than 200 feet. The project aims to reconnect crucial animal populations by providing a safe passage over one of the busiest highways in California. The history of this project is deeply rooted in the growing threat to local wildlife caused by urban expansion. The Santa Monica Mountains, home to a fragile population of mountain lions, have been effectively cut off by the 101 Freeway, one of the busiest highways in the country. More than 300,000 vehicles use the freeway every day, making it a death trap for wildlife attempting to cross in search of food, mates, and new territory. Since 2002, at least a dozen mountain lions have died trying to navigate this dangerous passage. One of the most heartbreaking losses was in 2013, when a genetically valuable mountain lion attempted to cross the freeway but was struck and killed by a vehicle. These tragic incidents, combined with the increasing evidence of inbreeding and genetic deformities in the isolated population, highlighted the urgent need for a safe crossing. In 2015, the Resource Conservation District of the Santa Monica Mountains proposed a wildlife overpass spanning 200 feet long and 165 feet wide, connecting the Simi Hills to the Santa Monica Mountains. This location was identified as the ideal site after extensive ecological studies revealed it as a natural wildlife corridor. The design of the crossing is a marvel of engineering and ecology. Unlike traditional road overpasses, the wildlife bridge will be covered with lush vegetation, mirroring the surrounding landscape to encourage animals to use it naturally. The construction plan involves soil-reinforced embankments, massive concrete supports, and steel reinforcements to create a durable yet environmentally friendly bridge. Engineers have designed the structure to withstand earthquakes, ensuring long-term stability. Wildlife fencing will also be installed along the freeway to guide animals towards the crossing, increasing its effectiveness. The total budget for the Wallace Annenberg Wildlife Crossing is estimated at $90 million, making it one of the most expensive conservation projects of its kind. The crossing is estimated to be completed by 2026. The Foothill Gold Line extension to Pomona is a critical infrastructure project advancing public transit across Los Angeles County's Eastern Corridor. Spanning 9.1 miles from Glendora to Pomona, this light rail extension is part of the Greater Metro L-line and is set to open in 2025. While it may appear straightforward at a glance, the engineering and construction behind the project are highly complex, involving heavy coordination with freight rail operations, multiple bridge constructions, and extensive utility relocation. Construction began with major site preparation along a narrow, existing rail corridor that had long been shared with active freight service. To accommodate the new light rail line without interrupting freight operations, the corridor is being fully reconfigured into a dual-track system. This requires precise grading, excavation, and the laying of new ballast, track ties, and continuously welded rail. Each segment of rail is delivered in long sections and joined using thermite welding, creating seamless tracks that reduce maintenance and allow for a smoother ride. One of the most challenging components has been the construction of 19 new or renovated bridges, including the San Dimas Wash and major street crossings. These bridges are built using cast-in-place concrete and large pre-stressed girders, set in place with heavy lift cranes during nighttime closures to avoid traffic disruption. Each structure is engineered for seismic resistance, using deep pile foundations and expansion joints that allow movement during an earthquake. At the station sites, Glendora, Laverne, San Dimas, and Pomona, crews are building elevated platforms with steel framing and concrete decks. The platforms are designed for level boarding, meeting ADA standards, and are equipped with modern canopies, real-time arrival displays, and integrated lighting and security systems. Underneath, utility conduits for power, communications, and signaling are buried in concrete-lined trenches, running the full length of the corridor. Electrification of the new line involves the installation of overhead catenary systems supported by steel poles and tension cables. Power is distributed from new traction power substations, which are constructed on specially prepared concrete pads and connected through underground cabling. These systems must be coordinated with the signaling infrastructure to ensure safe, efficient train operation. As of 2025, the extension is nearing full completion. When operational, it will not only connect the San Gabriel Valley more directly with Los Angeles, but it will also serve as a model of how to modernize and expand rail systems within dense urban environments while coexisting with freight rail and vehicular traffic. Cityscape Phoenix is a prime example of vertical urban integration, engineered to bring together office space, retail, hospitality, and residential living within a single, high-density, multi-block footprint. Situated in downtown Phoenix and covering nearly 3 city blocks, Cityscape isn't just a skyscraper complex. It's an intricately planned urban core designed to reshape how people work, live, and socialize in the desert metropolis. The structural engineering behind Cityscape is centered on a series of high-rise towers built atop a massive shared podium. The podium structure includes multiple levels of underground and above-ground parking, retail floors, mechanical rooms, and load transfer systems. Because of Phoenix's expansive soil conditions and high water table fluctuations, deep foundation systems were necessary. The engineers used drilled piers and mat foundations designed to handle significant vertical and lateral loads, particularly under the office tower, which rises 27 stories. Above the podium, post-tensioned concrete slabs were used throughout the tower floors. Post-tensioning allows for longer spans between columns, giving commercial and residential tenants more flexible interior layouts without structural interference. Shear walls and concrete cores, housing the elevators and stairwells, form the backbone of the lateral force-resisting system, essential for stability under high wind and potential seismic activity. One of the most technically demanding aspects was the integration of mixed-use occupancy. The office tower had to be acoustically and structurally isolated from the adjacent hotel and residential units. To achieve this, engineers implemented expansion joints and independent mechanical systems to separate vibration and sound transmission. Additionally, mechanical floors are strategically placed to house HVAC systems that serve specific building zones, ensuring that cooling demands are met without overwhelming the rooftop space. An important consideration in a city where cooling loads dominate year-round. Cityscape's central open-air plaza required careful planning to integrate the subterranean parking levels below it. Engineers created a post-tension deck system that spans the open public space, supporting landscape elements, lighting, and pedestrian walkways without exposing the parking structures beneath. Above, facade systems use curtain wall glazing, composite metal panels, and precast concrete to give the towers their signature modern look while incorporating high-performance thermal properties to reduce solar heat gain. Construction sequencing was a logistical feat. With 3 towers, multiple levels of underground parking, and active streets on all sides, work had to be staged vertically and horizontally, often requiring overnight concrete pours and precise crane coordination. Just-in-time delivery of materials was critical, given the tight urban footprint and limited laydown space. To Dallas, Texas, home to the stunning Margaret Hunt Hill Bridge, a modern architectural masterpiece. Named after Margaret Hunt Hill, a local philanthropist, the bridge is part of the larger Trinity River Project, which aimed to rejuvenate the central riverfront of Dallas with striking infrastructure and green space integration. Construction began in December 2005 and spanned nearly 7 years, culminating in the grand opening of the bridge in March 2012. Designed by world-renowned architect Santiago Calatrava, the bridge is the first of 3 Calatrava-designed spans planned for the Trinity River Corridor. While the Margaret McDermott Bridge was eventually completed, the third project was cancelled due to budgetary and planning concerns. The Margaret Hunt Hill Bridge, however, rose to become a centerpiece of urban evolution in Dallas. The most defining feature of the bridge is its 400-foot tall central arch, a stunning steel structure that can be seen from miles away. This arch towers perpendicular to the roadway, creating a powerful vertical statement against the flat landscape of the city. The main span stretches 1,206 feet over the Trinity River, supported by 58 white steel cables that twist from the peak of the arch to the deck below. These cables aren't just functional, they're architectural elements that give the bridge a distinct sense of movement and grace. The bridge provides 6 lanes of vehicular traffic, linking Woodall-Rogers Freeway with Singleton Boulevard in West Dallas, improving accessibility and reducing congestion. The arch itself is composed of 25 individual steel segments, assembled using 20,000 pounds of bolts and reinforced with over 450 tons of concrete. Its construction involved precision cable installations, segmental lifts using heavy-duty cranes, and reinforced steel connections. Every piece had to be engineered and installed with pinpoint accuracy, making it one of the more complex bridge projects in the region. Though the initial construction cost was projected at $117 million, later analysis revealed that the total project cost reached $182 million, including adjacent roadway improvements and design enhancements. However, the bridge also became the center of national attention in June 2020, when hundreds of peaceful protesters were detained on the structure during a police crackdown. The incident led to public backlash, prompting city officials to announce that no charges would be filed against the demonstrators. The Margaret Hunt Hill Bridge first opened in March 2012 with a celebration of parades, a street fair, live music, fireworks, and a ceremonial ribbon run as 40,000 people joined the weekend-long festivities. But we have to talk. The Delta Conveyance project is one of California's most complex and controversial water infrastructure efforts, aimed at modernizing the way water is moved through the Sacramento-San Joaquin Delta to serve millions of people across the state. At the center of the project is a proposed 45-mile-long tunnel, known as the Delta Tunnel, that will carry water from the Sacramento River in the north to existing aqueducts in the south. Engineered to enhance climate resilience and protect against sea level rise and seismic risk, the project is scheduled to begin major construction activities soon, with some early phase work, and permitting continuing through 2025. The core of the project is a single bore tunnel, up to 36 feet in diameter, buried approximately 100 to 150 feet below ground. This tunnel will be constructed using state-of-the-art tunnel boring machines designed to work continuously through variable delta geology, ranging from soft clay to dense alluvial soils. TBM launch shafts, which can be as wide as a football field and several stories deep, will be excavated at key access points. These shafts will serve as staging grounds for assembling the TBMs and will also house muck handling systems that remove excavated material as the tunnel progresses. The tunnel lining will consist of precast concrete segments, manufactured off-site and trucked in just in time. These segments will be assembled inside the tunnel immediately behind the TBM shield, creating a continuous waterproof lining. Each ring will be bolted and gasketed to ensure a watertight seal, critical to preventing groundwater intrusion in areas where the water table is high. Above ground, the project includes massive intake facilities near Hood along the Sacramento River. These structures will feature fish screens, sediment control systems, and pumping plants designed to divert water safely while protecting endangered fish species like Chinook salmon and Delta smelt. The intake channels will be constructed with engineered levees, erosion-resistant linings, and fish-friendly hydraulic features to minimize ecological disruption. Is the Kosciusko Bridge replacement one of the most significant and complex infrastructure projects in the recent history of New York? Stretching over Newtown Creek, this massive bridge connects Greenpoint in Brooklyn to Maspeth in Queens and plays a crucial role in the flow of traffic along the Brooklyn-Queens Expressway. The original Kosciusko Bridge, first opened in 1939, was a truss bridge built to carry just 10,000 vehicles a day. By the 2000s, that number had exploded to over 160,000 vehicles daily. Designed long before the interstate highway system even existed, the old bridge had no shoulders, no drainage systems, and frequent maintenance issues. It was outdated, congested, and structurally unsound. In 2009, officials made the bold decision to completely replace the 1939 bridge. The replacement project would consist of 2 state-of-the-art cable-stayed spans, making it the first major new bridge in New York City since the Verrazano Narrows in 1964. The first new span, the eastbound bridge, opened on April 27, 2017, initially handling traffic in both directions, while the old bridge was demolished. This was no ordinary demolition. The main truss span was lowered onto a barge and floated away, while the remaining approaches were destroyed in a controlled explosion, the largest bridge demolition in NYC history. Once that was cleared, construction of the westbound span began, and it officially opened to traffic on August 29, 2019. This span features 4 lanes, along with a shared bike and pedestrian path, a first for this crossing. Combined, both spans carry 9 lanes of traffic, LED lighting systems, and incorporate seismic reinforcements to withstand future earthquakes. Each bridge is anchored by 287-foot-tall pylons, supported by deep foundation shafts drilled 150 feet into the earth. In total, over 56 high-tension cables support the structure, with a total length of over 1,000 feet for the main span alone. The total cost is a staggering $873 million, making it the largest single contract ever awarded by the New York State Department of Transportation. The project also includes a transformative public space under the K Park, built beneath the Brooklyn approach of the bridge. This area features bike trails, green space, and performance zones designed to bring new life to the industrial area. Let's move over